This conference will now be recorded.
So like pumps are probably the most important thing that we got in our business, and it goes through everything. Water treatment, wastewater collection systems, even water distribution systems. They all use pumps, and there's usually some questions on all of those exams in regards to pumps. So I'm going to try to maybe share some information about pumps with y'all in regards to how they operate, some of the maintenance issues that come up with pumps, things like that. All right, I do have a couple of videos. I don't know if I'm going to get to them today, but I'm going to do my best to maybe talk about obviously pumps, valves, hydraulics. That's this section, and then after this, we'll get into electricity a little bit. There's a lot of engineering, obviously, that goes into pumps and how they operate. So let's get to it. All righty. So I'm going to throw up I'm going to start our presentation here. Oh, before I do that, let's take this off. I have the attendance spreadsheet on open behind the scenes, and you guys don't have to see everybody else's attendance besides your own. So anyway, so we're going to start talking about pumps. Like I said, very important, right, to all of our functions. And I see Josh Williams just arrived. So again, pumps and hydraulics, basically how to convey water from one place to another. And we'll get into some of the specifics about that. All right. I did send you guys a whole bunch of stuff. There was actually somebody in the class, and you know who you are, I think. I dumped a whole bunch of material on you all, presentations, some papers, some notes. I don't know if I sent you any videos, but anyway, I sent you a whole bunch of stuff on pumps and hydraulics because, like I said, it is an important thing. Understanding how these things operate and what they actually do. So I'm not going to go over all the material that I sent you, but it's a good place to start. So when the engineers are talking about certain things, maybe you don't understand all the specifics, but you know what? You at least, it's kind of like the babble of engineering speak. You might not understand everything they're talking about, but at least you have an idea of the language they're speaking, because there's a lot of that where you may listen to somebody and you're like, I don't know what the heck he's saying, but some of the terminology that we're going to talk about gives you a little bit of an understanding of some of the things operate. All right, and as far as maintenance goes, yeah, we are going to talk about some maintenance issues that are addressed in pumps. Let me just mute that so there's no background noises. All right, and then later.
Mr. Coop, I'm sorry to interrupt.
Sure.
Did you send a test? Did you send a test out this weekend?
Yeah, I did. Who's this? Wait a minute.
Adam, I don't think I got it. I gotta check my email again.
Yeah, please do. Maybe it's in spam. Because somebody else told me they didn't get it, and I resent it to them, so it's no big deal. I can resend it to you.
If you could, please.
Yeah, well, I'll do it after class, but November 4th, I gave you guys to do it. Some of you have already sent the answers to me, which I appreciate. But so is that Adam?
Yeah, it's Adam.
Adam Barno. Okay.
Barno. Yep.
Yeah. Okay. Because it's all right.
Thank you very much, Mr. Coop.
Yeah, no problem, my friend. No problem. And yeah, incidentally, kind of check your email boxes again, because like I said, I sent this presentation along with a bunch of other stuff on pumps and hydraulics. I sent you something on net positive suction head, which is something we're going to talk about later on when we get into the hydraulics and whatnot. Sometimes these emails end up in your spam folders, so if you don't mind, check on them. But there was somebody, their email put a stop. It rejected it. I got all of it sent back to me, and I tried to send that as individual pieces. If I have to, that's what I'll have to do in the future. All right. May lose service. Yeah, sorry about that. I hope it's good OT. But anyway, pumps and hydraulics, like I said, it's probably, well, it is. It's kind of like the most important thing that we got in the plant to move the water around, move the fluid around, move the sludge around, whatever you're doing, chemicals, all use the same type of machines, which are pumps. Okay, so, and then there are certain rules that we got to follow as far as how far, how high we can lift or send fluid. There's certain rules that we got to apply. All right, so like I said before, pumps, they're one of the most important components. Now, this says lift station, pump station. I want to differentiate that. People use them interchangeably, and that's fine. That's perfectly fine. Lift station, pump station. They do that. Both of them do that. But back in the day, it used to be very, very back in the day. A lift station was something where the water just was moved from one elevation to another. Right? And a pump station was something, again, would also move the water from one elevation to another, but would move it from one elevation to another and keep it enclosed for what's called a force main or something. Those rules really don't apply, but this was like way, way back in the day. And a good example of that at the IPS in the Passaic Valley Sewerage Commission. All right, the Archimedes screw pump station. They're huge, right? Everybody's seen them, they know they're huge. And but technically, it's a lift station. Everybody calls it a pump station. Where on the other side, the wet weather pump station is technically a pump station. Now, again, people use them interchangeably. You may see, well, it's a lift station. Fine, it's a lift station, it's a pump station. People use those terms interchangeably, and that's perfectly fine. But way, way back in the day, a lift station was, the differentiation was something that was just moving from one elevation to another and maintain, say, an open channel, whereas a pump station was the same thing, moving from one elevation to another, but it included a force main to be discharged down the road. Like I said, people use them interchangeably. So don't get confused by the use of both terms. They do both do the same thing. All right. But anyway, these are, like I said, one of the most important components, and not only in those applications, but pumping tanks, booster pump stations in the water system. But a lot of people maybe not, well, hopefully you guys do know a little bit about how they operate, but they're not really highly understood in general from the outside world. They are one of the least understood pieces of equipment. Okay. Now, there are different pump classifications. Actually, there's a few different pump classifications, but we're going to address two of them right here. And one of them is what's called a positive displacement pump. All right. Positive displacement pumps. When I say positive displacement pumps, one of the, and I have examples here, of course, but think about Archimedes screw pumps, progressive cavity pumps, diaphragm pumps, piston pumps, peristaltic pumps, rotary lobe pumps. Those are what are called positive displacement pumps, and I'll kind of explain why. Now, the other is called a dynamic kinetic pump. Most of us know that term as a centrifugal pump. Okay, and I'll kind of, there's different kinds of dynamic kinetic pumps. I know it gets confusing, but there's different principles behind those two pumps. All right, now as far as positive displacement pumps are, there is a fixed volume or a chamber inside those pumps, whether it's a piston pump, it'll have a cylinder. If it's a progressive cavity pump, there are spaces built in between the rotor and the stator. A rotary lobe pump, the same thing. A diaphragm pump, there's a fixed volume. Okay, and these act by forcing that fixed volume of liquid coming into the pump and forcing it through the body and forcing it out the discharge section. Okay, they do apply force to the water, there's no doubt about it, but they don't apply the same type of force that a dynamic kinetic pump or a centrifugal pump applies to the water. This is basically, with these pumps, it's garbage in, garbage out. basically regardless of the head pressure, as long as the pipes, gauges, expansion joints, flanges, if that can take the pressure, that fluid's going to go through that. And that's kind of one of the, it's actually both a downside and an upside with a positive displacement pump. They can make a lot of pressure. And the pump will continue to try and pump that fluid. It will continue to move that fluid through the pipe regardless of the pressure on the discharge side or the head pressure, until one of two things happens, actually a few things, until one of the, maybe one of the flange gaskets blow out, an expansion joint blows apart, or if it's a hydraulically driven pump like the Willett pumps in the Filthy Mess, when the hydraulic pressure of the oil matches the discharge pressure of the sludge, it'll stall. It can't go anymore, it can't push because there's no differential pressure between those two fluids. Or it'll amp out because there's so much current trying to go through that pump that it overheats because the coils just get hot because it's not moving the stator anymore, because there's just too much resistance, and then it'll geek out. We'll say it'll trip the breaker. Okay, so that's a positive displacement pump. Okay, they operate at slower speeds than dynamic kinetic pumps in general. Right? And now the other kind of pumps, dynamic kinetic pumps, the most popular, right? The most popular type of pump that we have. Okay, they basically apply a force to the water. They initially with kinetic energy, movement of energy. They're pulling water. They're motivating the movement of the water through the impeller or into the impeller, and then discharging it radially. And for example, a radial discharge, a centrifugal pump. And because of the movement of the water, the action of the impeller is imparting a force on the water. And you say it's centrifugal force, but it creates a decrease in pressure in the eye of the pump, which is the center of the impeller at the suction side. And then as that water is diffused out from the impeller, it's either through a volute channel or something called diffusers, which are kind of like little fins that aim the water into the discharge channel. That pressure is increased, and that resistance to that flow, it's got to go somewhere and it'll go out the discharge. So again, like I said, they operate by increasing the liquid velocity and converting this higher velocity into pressure by diffusing it through the discharge flow passage. And they can do it either by what's called the volute channel, which is an increasing size channel in reference to the impeller around the outside of the pump, or the impeller is dead center in the casing, and there are these little fins around the outside of the impeller, and it diffuses the water out into that channel. Okay, and then it creates flow. Positive displacement pumps, dynamic kinetic pumps. Okay. Now they operate at faster speeds than positive displacement pumps. For the most part, they will create a lot more volume. Depending upon the design of the pump, they can create pressure. They might not necessarily create as much pressure as a progressive cavity pump, but again, it all depends upon the circumstances. All right, so let's go back to positive displacement pumps. They could be a reciprocating design. This would be diaphragm pumps, piston pumps. I didn't mention plunger pumps. Plunger pumps and piston pumps are very similar, but the tolerances are different. The plunger pumps kind of, they float a little bit more in the cylinders than piston pumps. Okay, there's not as much clearance. It's still a disbursement. It's still, you're displacing that water, because the same volume of whatever's moving that water that's being pushed into the water is going to displace that water within the cylinder. Where you might find plunger design pumps, vac trucks, jet rodders, the Wuma machine is a plunger pump. Okay, it's similar in piston pumps, similar to a piston pump, but it's not necessarily taking up the entire volume of the cylinder as it's moving through that cylinder. Okay, I don't know if they've ever reinstalled the plate washer pumps in the filthy mess, they used to be plunger pumps because they can develop a lot of pressure. They might not necessarily develop a lot of flow, but they can develop a lot of pressure. But that's a plunger pump. So these are many times, and it depends upon the application. If I'm going to use a piston pump for an example, primarily for slurries, heavy sludge, things that might not go through a centrifugal pump that easily. But they're used for sludge, slurries, high density fluids. A good example of a positive displacement reciprocating pump, if you guys, and I think of PVSE because most of you are from PVSE. Of course, there's a large group from Jersey City, and then we have Passaic Valley Water on hand, but I'm going to reference the high pressure pumps. The high pressure pumps in Zimpro, they are reciprocating pumps. They're positive displacement pumps. They work in a little bit differently. There's basically, if anybody's ever seen them taken apart, and if you've walked with Zimpro, I'm sure you have, those pumps operate hydraulically, right? There's a hydraulic reservoir, right, which moves the hydraulic pump, which motivates more hydraulic fluid to go from the go into the bags. The big thick rubber bags are banded at the top and the bottom, and in the middle is this porous, this big metal piece inside with holes on it. What happens when the hydraulic oil is pressurized, right, with a piston? It's an interesting operation because the oil in the reservoir is moving a piston where there's hydraulic oil on both sides. And when that piston moves up, it's pushing the oil into that bag and expanding the bag within the cylinder. And it's basically, that's the discharge stroke. And then when the hydraulic oil, when the piston goes back down, the oil that's in the bag, behind the bag, is being drawn back into that cylinder, and it's contracting. And that's the suction stroke of the high pressure pump. And that piston going up and down, the hydraulic oil that's being pumped from the reservoir into the piston is pushing the piston up and down. It's a free flowing piston. It's only attached hydraulically between the bags and the reservoir. It floats basically on the hydraulic pressure. And when the hydraulic pressure pushes the piston, it pushes the oil into the bag, it expands, and it's discharged. And when that piston drops, and there's a four-way valve on top of that reservoir, which motivates the oil to go wherever it wants to. Now, those particular pumps have two sets of pistons and two sets of bags. Okay, and when one is stroking, the other's discharging, right? They're both stroking in opposite. So it is a reciprocating pump, but it kind of lessens the reciprocation a little bit. But there's also on those pumps, there are what are called accumulators. That's what they're called there. They look like torpedoes, if you've ever seen them. They're these steel cylinders, and inside those steel cylinders are also bags. And inside those bags, there is a pressurized, it's pressurized to a specific pressure to try to limit some of the surges from the reciprocation. I know from experience with those particular pumps, they still surge and reciprocate, and you can see that when they operate. But if one piston is operating if one piston is discharging while the other is intaking, that drop and surging should be less and less. That's just one example of a reciprocating pump. A chemical pump, if you've ever seen a diaphragm pump operating, and again, I have to go to Zimpro because that's kind of like my history, the spent solvent pumps. If you've ever walked through the breezeway and you hear, that's the spent solvent pumps. That's pumping the solvent, the acid, the wasted acid, the spent solvent. Actually, it's pumping it to the primaries, but that is a piston, a diaphragm pump. A lot of chemical feed pumps are diaphragm pumps. This is a fixed volume in that chamber, and that diaphragm, which is usually some kind of a flexing thing, and maybe Teflon, and it's sealed up around the outside, a piston pushes it in and out. It causes an intake and a discharge. Okay, a lot of chemical pumps, when you're putting the nitric acid from the acid tank into the solvent tank, you're using a diaphragm pump as well. A lot of the pumps that are in the chemical pumps, like in disinfection in hypochlorite, they may use what are called peristaltic pumps. They're not reciprocating pumps. They kind of maintain a consistent flow. Okay, because there's always one side is out open and pressurized to the discharge while the suction is beginning to fill. And I got a video on that. I'll show you what I mean. But piston pumps, diaphragm pumps, like I mentioned, high pressure pumps in the old heat treatment plant, Zimpro, those are reciprocating pumps. They all have to have some kind of an equalization of pressure, which is why it's those pumps, you hear them, boom, boom, because it's a pressure surge between the suction and the discharge stroke of the pump. So they usually have some kind of a surge tank, which in some cases they're called accumulators. The Willett pumps in the filter press building, I believe, unless they changed it, there used to be air pressure applied to the accumulators on those pumps.
They still do.
Really?
Yep.
Really?
The discharge sides, not the suction side.
Oh, yeah, yeah. But did anybody ever put sludge in the air receiver yet?
We have.
Okay. Every once in a while that would happen.
We've also had sludge in the MPW line, which overheated the Willets.
Nice.
Yeah, it's all fun, all fun.
Okay. Yes, yes. Yeah, so you have a little experience, obviously, with piston pumps. Obviously, check valves have to work. You know. But these are reciprocating pumps. These are the positive displacement pumps. The thing with these pumps, they can pump really thick stuff. I'm going back again in Vican tanks. There's progressive cavity pumps. Now, it used to be in the wintertime. I don't know if it still behaves this way. The density at the decant pumps in the wintertime there were times that we were getting that up to 20%, 18, 20% at the pumps. The progressive cavity pumps would have issue. It may be scale from the heat treatment units that we used to have to. They actually changed the pumps, basically, I guess, so we couldn't do what we used to do. And we used to do it with maintenance's approval. We used to put a chain wrench and bar the pumps over because they would get clogged up with this scale. Every time a Zimpro unit would do blowdowns, it would fill the tank up with this the scale, and it would jam up the pump. But in the wintertime, we would occasionally get the percentage solids up to like around 20, and the pumps would pump it, but they didn't like it, put it that way. But those Willett pumps in the Zimpro, in the filtering mess, they didn't care. They didn't care at all. 20% was like, this is nothing. You know, so these pumps, certain pumps can pump thicker, heavier solids than other pumps. And that's the reason certain pumps are installed in certain applications as opposed to some others. And that's one of those where a reciprocating pump, it has its upsides. It'll pump just about anything. It'll pump a slurry. It'll pump trash. But there's a surging that goes on in those pumps, unless whether you call them accumulators or you call them surge towers or whatever you call them, it's a means to try and dampen pressure dampeners. That's another term for them. It tries to dampen some of the excessive pressure that'll spike up and down going through those pumps. All right. And like I had mentioned, diaphragm pumps for a lot of chemical applications, feeding chemicals, metering pumps in the form of diaphragm pumps are very accurate. Because you know, if you get a metering pump that's a diaphragm pump, you know the volume, you know the limit, you know the specs on the pump as far as how big that chamber is, how much, say 100% stroke, say 100% pump speed, 100% stroke, you know how much it's going to pump. It tells you when you get the paperwork for the pump. So you can adjust it from there. And it's within a 1%. So you can exactly dose what chemical you need to feed. And a lot of times those pumps will come with, we call them calibration tubes. Looks like a big calibration. It looks like a big cylinder with markings on it, a graduated cylinder that's parked next to the pump on the suction line. And what you can do is you could fill up that cylinder to a point and take a note of what you filled it up to, and then cut off the tank and leave the pump on and open up the calibration column or the calibration cylinder and, you know, take a watch and see how much the pump is pumping at a specific setting, so you can maybe adjust it from there if you need to. But those are metering pumps. I'm trying to think. Again, going back to VSE, and I apologize for you Jersey City guys and Save Valley Water, but if you work with any chemical feed pumps, you maybe have an idea of what I'm talking about. But the thickener scrubber system, those are peristaltic pumps. Those are not diaphragm pumps. The thickening centrifuge scrubber system, I mean, there's one in the thickeners and there's one in the centrifuge, and the feed pumps are on the west side of the main floor. In Zimpro, they have, unless they changed the pumps in 4 years, which they could have, they were diaphragm pumps that were used to feed the chemicals, the hypo and the caustic, to the scrubber upstairs. And you can walk by them and hear them. I don't know, years ago when I was in oxygen production, for an example, the cooling water chemicals that we would feed to the cooling water system. We had little drums and little diaphragm pumps sitting on top of it, and you would feed the chemicals into the cooling water system. And you go by and you hear, that's diaphragm pump. Those are metering pumps. Okay, but the first one I want to talk about is what's called a progressive cavity pump. I have a video. Hopefully it's going to play. It's a cutaway, and there's some weird music that goes along with it, but it's actually a pretty good video if you've ever tried to figure out, hey, how does this thing work? You know, it's got this little corkscrew looking thing inside of it. And then there's a flexible stator, it's called. So the rotor has this corkscrew looking thing in it. And the stator is usually the softer, not too soft because it'll tear it up with debris and grit, but it does have some flexibility. And what happens is there's spaces in this little corkscrew thingy, in this rotor. And those spaces are known. So as this rotor turns, it's moving the fluid through the cylinder. All right, and it is good for some pretty heavy duty stuff. It can pump, well, let's see. Like I said, in decant, those pumps will do like 20% before they start to glitch out on you. Depending upon the season, the thickeners, you may get, I mean, in the wintertime, I guess you could get about 3, even possibly sometimes 3.5%, 4% solids coming out of the bottom of the thickeners in the wintertime. And that's when you debate about shutting the centrifuges off. But those pumps discharge into the south well where the centrifuge feed pumps are in the basement. Those are also progressive cavity pumps. They're just huge ones. All right, now they're going to pump that stuff upstairs, but they're pumping it at 3.5%, 4% solids. And then it's funny because on the other side, on the north well, you have those centrifugal pumps, but they're open impeller centrifugal pumps, the low pressure pumps, but they constantly feed a pressure to the loop, and then the high pressure pumps take it off there. So that's the only not out of place pumps, but those pumps that are on the low pressure pumps, they're centrifugal pumps, and they're going to feed the sludge loop, which is actually 2 loops that go around Zimpro, and then the high pressure pumps come off of that. Actually, it's multiple loops because there's the loop is in bays from the, anyway, I don't want to get into that. You guys can go and walk through the building and look up at the ceiling and you can see what I'm talking about. But that's called a sludge loop, just like there's a sludge loop in the thickener building. But progressive cavity pumps are, they will pump against the head, which basically is resistance. They will keep pumping against the head, regardless of the head pressure. And that's why they will have shutoff switches on the discharge side, because they're going to want to keep pumping until they have some kind of an electrical meltdown, because there's just too much power that's being applied and it's not going anywhere. And of course, if you shut a valve. Some doesn't blow up. They will run until they blow up. But there's basically 5 main parts. And I know you say, well, there's more than 5 parts. Yeah, that's true. But there's basically the housing, which is the casing. And then inside that casing is a stator. It's usually a softer material. And then that rotor, which is that corkscrew looking thing, it's usually made of maybe stainless, maybe it's hardened steel usually, but it's chromed possibly to make it smoother. And then of course there's a little bit more than that, but there is a connecting rod to the drive shaft. It kind of runs, kind of wobbles when it runs. And of course, yes, there's a ball gear in there, and obviously there's bearings and there's seals and there's all kinds of other stuff. But it can be either like chrome plated tool steel or stainless steel. It's usually smooth. If it's not smooth, then it's going to lose performance and it may become abrasive to the stator. And that happens sometimes, that the rotor gets scratched up, and if it's especially if some of the material is a little excessively abrasive, it'll wear out the stator. These pumps cannot run dry. Progressive cavity pumps have to have fluid in them. Okay, I'm trying to think where else. PVSC. Oh yeah, the storage pumps. The storage pumps are now all progressive cavity pumps, right? The sampling pumps at PVSC are progressive cavity pumps because they'll move against the head. They'll operate against the head. The stator is made of either natural rubber or other synthetic material, and I know they're completely different pumps now than they used to be. But we actually had to change the specifications of the stators because we were tearing them apart. And the stators, I can't remember. Actually, everybody that was involved in that is now retired. Gene Liswan's retired, Bruce Green's retired, and of course I'm retired. But we were tearing pumps apart. We replaced, I think, every pump in Decant twice during one particular year, and it was just getting worse. And they're not supposed to tear up that fast. They're supposed to last a while. And it was because there was a lot of excessive grit and scale in the sludge. I mean, you got to wash the units, and you got to blow the units down. You got to blow the reactors down, and all that scale got to go someplace. It goes into decant tanks. But we had spec'd out, of course, with the I remember, was it Hisco pumps? I don't remember, but to change the stator, a little bit stronger stator so they didn't tear up so easily. Because once the stator's torn and the rotor's scratched up, it loses effectiveness as a pump. It won't pump as well. So that was done. And now I think, I don't know if all the tanks have them after 4 years. When I left, we had, and John Maya was involved with this. He was kind of the lead guy, I think. I don't know if he came up with the idea, if somebody else came up with the idea, but I remember we went to the contractor, somewhere in Union, I think it was. I don't remember. But they got these, they're like grinders, but they're designed to bust up the rocks, bust up the scale, rock breakers or whatever on the suction, to break up that scale so that it didn't get jammed up in the pump, because it was so, because those were the things that caused a lot of problems with those progressive cavity pumps. But the stator has to be made of something a little bit flexible, because basically that rotor, as that corkscrew makes its way through the pump, kind of slides over that stator, and then those pieces. I know, and like I said, I got a video of it. I'll show you. And again, it's determined by the application, the rotor and the stator. But again, these pumps, depending upon the pump and how long the rotor is, and how many stages, because that's how they assume it. Every complete stroke, basically, of a rotor, if you do that a couple of times throughout the pump, even though it's a single shaft, it's called staged. They stage it. You can develop quite a bit of pressure. All right. In operation, again, the liquid travels in the spaces between the rotor and the flex. The rotor revolves rapidly, and capacity is directly proportional to the rotor speed. and the pump size. So if you know, and these come with the manufacturer, if you know the volume in that casing in that between that stator and that rotor, the openings, there's a direct correlation between the RPMs of the pump and how much it's going to flow. So not as opposed to like a centrifugal pump where the pump's applying a force, the flow can be varied based on the pressure. Whereas a progressive cavity pump, the only limit on that is the specifications of the stuff downstream. In other words, like if you have a pressure specification on an expansion joint, or a gauge might blow off, you know, or the flange gasket may pop, or somebody closes a valve, you know. That's why they have pressure switches on. The pressure switch should shut the pump down. And it's really a physical switch. There's just a tube with a plunger, and it's basically just a little springy switch. When the pressure pops up, it pops the switch and opens the circuit and shuts the pump down. It's better to do that than to cause damage. Okay. But this rotator will continuously groove. And again, the flow is in direct proportion to the pump speed. So if you know the specifications and you know the pump speed at 72%, you know what that pump's going to pump. Okay, at 40%, 50%, that's what that pump's going to pump, regardless of the resistance or the head pressure on the discharge side. It should be the same. Okay. And incidentally, if anybody's ever, I don't know how familiar you guys are with the Zimpro plant and the heat treatment, and I apologize, I'm just talking because this is where I came from. This is another way to calculate flow, and I know I'm talking about a reciprocating pump. The high pressure pumps in Zimpro, those flow meters that you see on the SCADA that tells you how much flow is going through the Zimpro unit for each individual pump, it's not measuring the sludge flow. If you guys were aware of it, it's measuring the oil flow. It's measuring the oil flow because the flow through those cylinders is directly proportional to the flow of the sludge. And so that's where that calculation comes from. Okay. Just to let you know. But anyway, these progressive cavity pumps, it produces a non-pulsation flow. It's a more continuous flow. I said this before, this is absolutely true. They will burn up. You do not run them dry. Progressive cavity pumps, they have to have something in them because that stator will fail. It will weaken because that rotor is rubbing against it. And if there's no fluid in there, it will heat up and it can actually like melt it or burn it. The stator will fail. As opposed to a piston pump you can run dry. Just that. All right. Progressive cavity pumps will handle a wide range of fluids from clear water to thick sludge. That is absolutely true. So I'm trying to remember what this one is. This may be, yes, this is a cutaway of a progressive cavity pump. I think it's a neat little video. All right, I'm going to stop it right there just for a second. Okay, so you can see the cutaway. Now, obviously, they had to make a cutaway if they wanted to show this with plastic, let's say, front or plastic window, so you guys could see how the action is. And you can see the action. You see as the screw turns, the little thing, it looks like it's moving forward. Whoops. So there's a slight eccentric movement to that shaft. It's not spinning true center. It's off to the side a little bit. And that action of that rotor is moving that fluid through that space, through those cavities. So that's a progressive cavity pump. Okay, we've got them all over the place, usually in sludge application, but they can be used for lots of different things. I'm trying to think of another application. Centrifuge polymer pumps many times are progressive cavity pumps because the polymer, the snot that you're pumping through the pipe is really thick, especially in the Dynablend, what's called application, where you're activating the solids in a small space. In order to feed that, you're going to continuously feed that into the Dynablend tank where those polymer solids are activated and those molecules open up so that they'll be able to receive the opposite ions of the solids that are contained within the water. Right? So that's a progressive cavity pump. Sludge pumps, for high head applications, they're really good. Like I said, the sample pumps, if you guys have ever had, then this is not all pumps. I'm like I said, I'm going to where I used to live in the PDSA. If you go into the finals, in the finals gallery, right off the tunnel, you'll see, actually, yeah, there's pumps there. I think it's by the elevator, the freight elevator. Those are sample pumps there. So those particular pumps, I believe, are the primary effluent sample pumps. In the finals, in the gallery, there are pumps right there. They're sample pumps. Those are the mixed liquor sample pumps. They send their samples to the O&M building sample room. Got quite a distance to take it, but they'll keep doing it. And in the tunnel, just west of the thickeners, between the thickeners and the EPAs, I don't think it's quite, that's actually on the right-hand side, if I remember. There's sample pumps there too. That's the effluent sample pumps. And they pump their, what they sample out of the, into the O&M sample room as well. So progressive cavity pumps are probably all over the place by where you are, and you don't even realize it. All of the thickener sludge pumps are progressive cavity pumps. The decant pumps are thickener are progressive cavity pumps. The polymer solution pumps that feed the Dynablends are progressive cavity pumps. So they're all over the place. All the sample pumps are progressive cavity pumps. Next one is an Archimedes screw pump. It's basically a channel, right? It's a big U-shaped channel on an angle where there's a big screw inside, a rotating screw. So they call them screw pumps. Archimedes, I think he was a Greek dude. Not sure when he lived, but he basically invented this thing. And back then it was like a hand crank the water from the river up into the fields to irrigate the farms. Sometimes there'll be enclosed cylinders with the screw conveyor inside. And yes, these are positive displacement pumps. These pumps will only pump based on the RPMs and the space, the channel space of this trough. And this rotating screw fits in it. And yeah, the tolerances are kind of close. If you look at the IPS for an example, the tolerance there is pretty close. That's why that bottom bearing is so important in those influent pumps, because it's holding up the screw. There's a bearing on the top and there's a bearing on the bottom. And when I worked over there in the early 80s, one of the big jobs that we were supposed to keep track of, we were supposed to go down and open up the grease cock to make sure grease was coming out of that bottom bearing. Right at the bottom of the stairs, there used to be, I guess it's still there, a little valve to open up to make sure the grease was coming out, so you can prove that the grease was making its way to the bottom bearing. Because if that fails, the screw would drop into the trough, and it's going to take a little while before the screw starts to shut off and you'll tear the screw up. But it's basically, like I said, a U-shaped channel, and this rotating screw, this giant screw, fits closely into it. any angle, and up to 45 degrees. And this literally screws the water uphill from the lower level to the higher level. The screw does not develop any pressure other than height or head pressure. It's basically a conveyor. And this is a little video. This is not from PVSC. This is just a random video of a Archimedes screw pump, especially for those folks who've never seen one. Kind of looks very similar to the PVSC type pumps. These are used a lot of times for stormwater control. All right, it's an open channel. It's a progressive cavity pumps. These things are pretty cool. What they pump is based on the level. What these pump is based on the level. In other words, that screw is going to chew up more water if the water's deeper on the suction side. So more water is going to make its way up that screw. And I know it looks like a lot of it's falling back, and yeah, some of it is, but that force, a lot of that's also getting carried up the screw and dropped into that higher elevation. Now, if that water is shallow, that pump's not going to pump as much. If the water's deeper, the pump's going to pump. Okay, so that's an Archimedes screw pump. They can do a lot with less as far as power goes. They're usually geared. There's a gear drive, a big gear drive there. So the motors maybe aren't as big to move that as much water, but you need the space in order to use them. I'm trying to think. I know PVSC has Archimedes screw pumps. In the other class, there's people from Rahway Valley Sewerage Authority. They have screw pumps. Their screw pumps are on their effluent side. They're around. They're definitely around. All right, so let's go back to the reciprocating pumps. I mentioned it. I talked a lot about it. The piston pump is one type of positive displacement pump. It just, again, it works like the piston in an automobile. There's an intake stroke and a discharge stroke, and in between there's ball check valves. Usually ball checks can be swing checks, don't matter. On the intake stroke, the intake valve opens, fills the cylinder with liquid. As the piston reverses direction, the intake valve is pushed closed and the discharge valve is opened. The liquid is pushed into the discharge pipe. Diaphragm pumps are also reciprocating pumps. They work very similar to piston pumps, only they're not piston pumps. They work on a diaphragm. There's a flexible diaphragm that moves in and out. They're composed of a chamber used to pump fluid, a diaphragm that is operated by either electrical, mechanical, or pneumatic means. And again, there's two valves. There's a suction check and a ball check, a discharge. I always say ball checks because I always associate these pumps with ball check valves. They all seem to work on ball check valves. The difference between that, a ball check is just that. It's a ball that sits in a chamber, usually on some kind of a seat or a cage. And when the intake stroke opens, it opens. And then when the stroke goes down, it closes. And the opposite is for the discharge side. So they're kind of placed opposite in their configuration. So when the piston moves, like a piston, for the Willett pumps, the pistons move up, the ball check is going to lift above the suction side and let it go in. And then when the discharge side drops, that ball check drops back down into the seat. And then on the discharge side, it conveys just the opposite. The ball is pushed open when the other flexion valve is pushed closed, and it's transported out that way. Okay, diaphragms kind of work the same way, diaphragm pumps. These flows are very accurate with the diaphragm pumps for chemical feed. And they can pump a lot of crap too, depending upon what the diaphragm is made of. The diaphragm pump is a variation of the piston pump, like I just said, in which the plunger is isolated from the liquid, being composed of a rubber or a synthetic diaphragm. Usually a synthetic, especially chemicals, it's probably not going to be just plain rubber. It's going to be some kind of elastic synthetic. As the diaphragm is moved back and forth by the plunger, liquid is pulled into and pushed out of the pump. Diaphragm pumps are frequently used for chemical feed pumps, and I just mentioned that. I talked about that already. By adjusting the frequency of the plunger, which is the speed and depth of stroke. All right, a percent of speed, depth of stroke. You can control the flow. And this is a commercial. A lot of the videos that I show are commercials. And this one is not necessarily for a chemical feed pump, but it is for diaphragm pumps. I believe it's a pneumatically controlled diaphragm, I believe.
Safety, innovation, efficiency, reliability, value. That's what you expect from the world's premier positive displacement pump, and what Aero by Ingersoll Rand has delivered for over 80 years. As a market leader, Aero has paved the way with products that help customers succeed in a changing marketplace. Our Expert Series air-operated diaphragm pumps underscore that commitment with superb fluid handling, matched by the industry's best total cost of ownership. In addition to protecting your budget, the EXP line includes patented design features that safeguard your most valuable asset, your workforce. For unsurpassed structural integrity, EXP pumps have more bolts than the competition, and exclusive dome-shaped ribless caps that prevent hazardous leaks and keep fluid in the pump where it belongs. Our 2-inch EXP pump houses even more safety details, like 1.5-inch thick casing and vinyl ester thermoset caps that form a virtual shield between your equipment and your crew. Innovation built into the EXP's exterior can be seen inside as well. Let's take a closer look at our patented valve system that yields high performance and steady operation. As compressed air enters the pump, it pushes the diaphragm against our unique simul-shift valve, which maintains an ultra-positive signal to prevent stalling. The simul-shift valve also assures faster trip over for continuous flow with minimal pulsation. Once the diaphragm chamber is pressurized, quick dump valves block icy air from entering the major valve and promptly exhaust the air so the pump never stalls or freezes. This allows the EXP to cycle faster for exceptional performance. To keep things running smoothly at all times, our ceramic inserts control airflow for maximum efficiency, all without lubrication or maintenance. Combine this with cutting-edge process intelligence, and you have a diaphragm pump that's revolutionary. A pump that offers unbeatable energy efficiency and non-stop operation. In fact, tests performed under the strict guidelines of the Hydraulic Institute of America prove the EXP to be up to 40% more efficient than competitors. This efficiency reinforces our goal to help customers reduce energy costs, consumption, and emissions for a greener workplace and a greener world. Outstanding reliability and durability compound our green efforts by minimizing waste. Thanks to smart engineering and on-site testing, the pump's convoluted diaphragm lasts 4 times longer than traditional pumps, while a modular design affords easy maintenance and repairs. The EXP also spans a full range of port sizes, from 3/8 of an inch to 3 inches, plus a full line of specialty pumps, including FDA-compliant material pumps, flat valve pumps, powder pumps, and 2-to-1 high-pressure pumps for more viscous fluids. With so many options, it's no wonder Aero pumps stand apart, especially when the purchase price is the smallest piece of the cost of ownership pie. When you total the cost of energy, downtime, parts, and labor, you have a lot to digest. But with its low maintenance design and minimal energy use, the EXP brings the slice of ownership down to a more palatable size. It all adds up to renowned performance and lower costs, backed by our worldwide service and exclusive 5-year warranty for worry-free operation and long-term value. To learn more about how the Expert Series can breathe new life into your operation, visit IngersollRandProducts.com.
So like I said, this is the commercial. And that's all right. They got to sell its stuff, and I'm not going to fault them for it. But the principle that I wanted to show you guys is how these pumps operate. All right. When that diaphragm moves forward into that chamber, there's only so much room in that chamber. Okay, and there's only so much space. So if there's fluid in that chamber, some of it's going to have to go. And that's what the displacement is. You fill up your bathtub, right? And you go and sit in the bathtub. the water level goes up. So you gotta make sure you don't fill the water up too much in the bathtub. So when you go in the bathtub, you know, for us, like somebody like larger like me, I may overflow the bathtub because the water's gonna go up so high because there's only so much space in that space. There's so much volume in that space. And when I put my big body in that tub, the water's gonna fill up and overflow. That's how a positive displacement pump works, whether it's a progressive cavity pump, piston pump, diaphragm pump, or what's called a rotary lobe pump. And then there's this guy, peristaltic pumps. These are actually pretty cool little pumps. Sometimes they're called hose pumps. They have a series of rollers to compress the plastic tubing to move the liquid through the tubing. And it's interesting. So these rollers on this rotor, they squeeze the tube. And you would think that those tubes would wear out. Whatever they make the tubes out of, it's specified so that they don't wear out that often. They just still have to be maintained, but they don't wear out that often. Right? A rotary gear turns the rollers at a constant speed to meter the flow. The peristaltic pumps are mainly used as chemical feed pumps, which they've kind of taken over a little bit as far as chemical feed pumps go, because you don't get the, it's more of a consistent flow than a pulsating flow. And I have a video to show you how they operate. They really came out of the medical industry. And I'm trying to think, peristaltic pumps. I mentioned the scrubber system in the thickener building, second floor, peristaltic pumps. The disinfection and NPW pumps at the EPS are peristaltic pumps. A lot of chemical feed pumps are peristaltic pumps. When just before I retired, we were doing a project. We had to shift the plant flow to the chlorine contact tank, and we needed to dechlorinate the water. We had purchased sodium bisulfite, and we purchased peristaltic pumps and wired them up on top of the chlorine contact tank and fed the sodium bisulfite to the chlorine contact tank. We also had to put the defoamer in, and the peristaltic pump actually, the defoamer was too thick. We actually used a barrel pump. I'm trying to remember who was doing that. Demetrius. I don't know if he's still there. Demetrius Johnson he was my guy on top of the chlorine contact tank. Jeremy was involved in that. He actually was the guy that went out and bought most of the stuff associated with that project. But Demetrius was up on top of the chlorine contact tank, and when the foam would come up, it's like, okay, crank that oil barrel pump and add some defoamer to it, and it would kill the foam right away. But we had set up a peristaltic pump up on top of the edge of the chlorine contact tank so we could dechlorinate the water going to North Bay. That was that was like just before I retired. I'm trying to remember why we did that. I think we did it because we were sending a diver into the main effluent conduit by the head house. I'm wondering if that was when he had to put a plug in. Yeah, I think it was because he had to walk up the main effluent conduit and put a plug in to the water line that ran to the old chlorine building. Because the old solution water line for the old chlorine building, there was no way to isolate it. It came right off the conduit, the main effluent conduit. And they had to, I think they had to cut it out or something. So it was either dig up the street, and the pipe was like 20 feet down, or plug it. And we brought a diver in, and he walked up the effluent conduit towards the effluent control chamber from the head house, and put this plug in that pipe so they could do the work in the basement of the old chlorine building. Anyway, that's what they were there. But peristaltic pumps was the pump of choice, at least to feed the sodium bisulfite into for the dechlorination chemicals. And a lot of chemical feed pumps are now peristaltic pumps. And it's really just changed by the speed. The volume of the known area of that tube between the rollers, or the volume between the two rollers on that tube is known. So the RPMs is going to be equivalent to the flow. Or you could change the size of the tubing if you need to increase it. And this is a little video showing how they operate. There's no audio, no music, no catchy conversation. So you see this opens up, right? And this is pushing the fluid through it as this rotor squeezes these hoses. All right, do it again. So the rotor is squeezing the hose. All right, and it's moving this measured volume, right? Let me go back just a little bit. Just a little bit. All right, say here, whoop. All right, we'll stop it right there for a minute. The volume of fluid between these two rollers on this side of the hose is known. So however many times this rotor is rolling around, it's measurement of flow. All right, that's enough of that. I've seen that about 53 bazillion times. So there's a pump we don't see too often, at least. You guys may see them out in different applications, but it's called a rotary lobe pump. Now, I don't know how many car guys we have in the class. I'm sure we got a few. It's like, well, where do I see a rotary lobe pump? It's based on the same design as a supercharger. If you have a rotary lobe supercharger on a car, it's a rotary lobe compressor. There used to be compressors years ago at the head end that were rotary lobe compressors. They were used for pre-aeration. They never really worked right, so they were supposed to bubble the grease and scum up in the head end and push it up, and we were supposed to burn it in the old incinerator building. Never really worked right, but at any rate, those pumps, those styles do exist, and I think I just have a video to show you all. Yeah, I think this is just a video, and I'll let the operation define it, and you can see for yourself. Again, it's another commercial. So if you follow the little beads inside this animation, as the fluid's coming in on the left, these spaces in the lobes between the lobe and the wall, that volume is known. So the RPMs, again, that known volume of when these lobes are open to the outside is known, and it could be proportional to the flow. Where have I seen these? You guys probably don't recall. Tony's not with us tonight, but he may. Well, you know, he got the recording. I don't know if actually it's October 29th. We're almost getting to the anniversary of Sandy. October 29th, 2012, when Sandy decided to come through and pay a visit, the plant, PVSE was wiped off the face of the earth, pretty much. The storm surge came up from North Bay, up Wilson Avenue, and then up the creek between what used to be Whitco, that's now PVSE's property, and PVSC by the tank farm there, and it kind of just filled up Lote Street and wiped out the plant. The water just came in from all over to the point like there was like 3 feet of water in security. The cars, security's cars were floating at the head end. If you went by the warehouse, it was, well, let's put it this way, it was deep. All right, and all that extra water, that salt water flowing into the finals, filled up the finals to the point where there was a plug in one of the finals because there had been a small leak, and this was supposed to be a plug to prevent the finals from flooding the gallery, blew out. And it flooded the whole wet side gallery all the way up to the street. And in Zimpro, when the storm surge came in, it flooded out the filthy mess up to the first floor. And it also flooded out Decant, and then that water flowed into Zimpro and into the thickeners. And I'm saying this because it's anecdotally. I wasn't there that night it happened, but I heard, and they told us don't bother trying to come in. They let us come in a few days later because we had a lot of work to do. When I came in to actually check to make sure that the generators and the pumps were working to pump out the gallery, pump out the tunnels. When I saw the flooding in Zimbro, the water was, well, over the packs. The packs, you couldn't see the packs. It was just water. And then, as days went on, weeks, it was pumped out. But at any rate, to get the sludge, once the water was out of the basement, and maintenance did a really tremendous job that whole time we were there. Well, operations was too. We were there cleaning up and pumping down and changing out pumps and moving things around, trying to get it. Once they got the water out in the basement of Zimpro, they got the pumps to working in the thickeners, because the thickeners is higher than Zimpro. So they got the pumps to working in thickeners. We still didn't have the pumps in Zimpro, I should say. But what they did have was contractors. I believe, I'm not sure if it was, I think it might have been SpectraServe. I don't know, it wasn't SpectraServe. Maybe it was Willebrator. I'm not sure who the company was, but they had imported centrifuges from like all over the country. Because I remember I spent the night working with these guys, and a couple of nights actually, and they were from all over the country. It was guys from like Oklahoma, Arkansas, Texas. They came from all over. They set up like 10 centrifuges where the parking is by the thickeners. And they had big 4 or 6 inch submersible pumps in the wet wells. And they were pumping to a well that they had set up. And they had these kind of pumps feeding their centrifuges, rotary low pumps. And they were, we're making cake so we could pump the sludge out of the plant, get rid of the sludge in thickeners, and then get rid of the sludge in the decants. It took a while, but because when the plant shut down, everything just stayed there. I remember walking with a contractor through the tunnel to the primaries. No lights in the tunnel. We had flashlights. And just to make sure, of course, we had boots on just in case we ran into some water because, the elevation changes. But when we came up by the primaries, because I needed to show him where to go in the primaries. And then when we came up, I was walking back and it was like, you could see the birds walking on the primaries because the sludge was so thick. So the priority, of course, was to get rid of the sludge before we could get the plant back in operation. At that point, the water was just kind of flowing through the plant and being disinfected. But the point I wanted to make was the contractors that they called in, and I'm not sure who it was, and it wasn't SpectraServe. It must have been Willebrator. I don't remember, but they brought in centrifuges from all over the place and set them up in that parking lot by the thickeners. There were 10 centrifuges. They had a well, and then they had these pumps as centrifuges.
Mr. Coop, did you guys try to reactivate old centrifuge as well?
They did. Yeah, as a matter of fact, your boss, well, I don't know if he's your boss, Craig Spencer?
No, I have John DeCosta by me. I'm in Filter Press.
Well, like the boss.
The big boss.
He took Bridget's place.
I'm not too sure.
But he was over there, Craig Spencer. He was the guy. They brought him in, and they rerouted some piping, and yeah, we got the old centrifuge to work. Once they got the pumps in Zimpro to work, they didn't work that long, but they got them. They got a couple of the fuges to work just to get rid of the sludge.
I heard it was a couple, like maybe a month or two.
Maybe, yeah. We got
and it wasn't good either. I heard there was like white clouds and stuff going off. It wasn't the greatest.
No, well, way back in the day when the old centrifuge was online, there were a lot of white clouds because the line was just out of control. That's why I hate working with line. But it ain't right. But yeah, no, Craig Spencer was the guy. He actually came in, and another ex-PVSC guy who retired, another guy, Chris Katina. John DeCosta probably knows who he is. He remembers him. He actually came back. They called him up. Can you come in and help us? Because he used to be the guy there at the old centrifuge. And they worked. They hired him to help put the centrifuge back together again to get it working right. But the outside contractor had these pumps as their centrifuge feed pumps. They worked fairly well. They were fairly portable. They're a continuous flow. Like any other like any other positive displacement pump, you can move a lot of stuff through them. I mean, because these two sets of gears, they kind of enmesh with each other. There may be some issues, but it's a rotary low pump nonetheless. So there's a lot of versatility as far as what engineers can do. Okay. So as you can see, like I said, it looks like it doesn't work that well, but they actually work fairly well, moving the fluid. And like I said, this is a commercial. It's not a pulsation flow, it's a continuous flow. So there's lots of different options, right? And obviously, choosing what pump and why has a lot to do with the material. Like these rotary low pumps, they were chosen by the contractor. These guys preferred to work with these pumps. Could they have used a progressive cavity pump? Yeah, probably. But they chose to use rotary low pumps, which is fine. Progressive cavity pumps and rotary low pumps have a lot of the same characteristics as far as how much they move. Rotary low pumps maybe are a little more forgiving as far as letting them run dry. Whereas a progressive cavity pump, the rotor is physically rubbing against the stator. They have to run wet. These do too, but they're a little bit more forgiving. As far as a piston pump, you could probably pretty much pump sand with them. You know, so that's the distinction. Again, the problem is the reciprocating flow. You need pulsation dampeners or accumulators, as they're called, to balance out the pressure so you don't blow the pipes apart. They do shake. It's not a consistent flow, it's a pulsation flow, which is why a lot of the peristaltic pumps for chemical feed are kind of taking the lead from the diaphragm pumps in chemical feed pumps, because it's a more consistent flow. It's continuous, it's pulsation. Okay, so but a lot of it has to do with the amount of solids that's in it. Usually the higher amount of solids, more intense of a positive displacement pump you're going to use. You know, like if it's real heavy sludge, real thick sludge with maybe some debris in it, you might want to use a piston pump. Progressive cavity pumps can handle some dense sludge and can handle a little bit of debris, but if there's more abrasiveness to it, there may be some problems with progressive cavity pump. Well, quite personally, there was an operator that dropped a walkie-talkie in one of the thickener tanks about 15 years ago or so, maybe 10 years ago. It was never recovered. So it obviously went through one of those pumps, because those tanks have probably all been taken down and cleaned at least once in the last 10 years. So it went through that pump. You can go to some places and plan, I don't know if it's still that way, but the rings in Zimpro, shoot, can't remember what they're called. See, 4 years out and I forgot. When at the pressure control valves, when the high pressure sludge goes through the pressure control valve, there is a place, it's a lead plug that's sitting in the bottom of the PCV area, right? And it's designed to absorb that pressure. Now that part of that lead seat, there is rings that hold it in. And there were, from time to time, they would end up in the decant tanks. I can't remember what they were called. Oh, shoot. It's supposed to dampen the pressure. It's supposed to give a place so that pressure hits a right-hand turn or whatever, makes it turn, and it hits this lead to disperse some of that pressure. But at any rate, there's seating rings in there, and they're heavy. And I've seen them broken in pieces. I've seen a few of them, half of them in the Filter Prince wet well. They also used to, you'd be walking in the decant tanks and you would hear this metallic noise going up one of the elbows, and then it would be falling back down. I have seen them go through the pump. So they can handle a lot of stuff, but they're not primarily designed to handle that. Somebody told me one time a 1-inch nozzle went through one of the pumps and thickeners. They could hear it. They heard it went through the pump. So, I don't know how much longer after that they had to rebuild that pump, because it probably damaged the stator and the rotor a little bit. But they're usually used for real thick, heavy flows that have a lot of debris in it. Now, the other side of the coin, the dynamic kinetic pumps or the centrifugal pumps, which is what I'm going to talk about here, they're not necessarily, they're not necessarily designed for a lot of debris and heavy sludge. There are some that are. But you can see that they are not as efficient in that regard. They will move a lot of flow, not necessarily at a higher pressure. Now, centrifugal pumps, radial centrifugal pumps, can be designed to handle a little bit more pressure, but their flows is not continuous based on the RPMs. It's based on the head pressure. If the resistance against that pump is high, the flow is going to be low. If there's a higher discharge pressure or a higher head pressure, the flow is going to be low. If the pressure is low, the flow is going to be high. Okay. Now there's different types of dynamic kinetic pumps, and I'm going to get into them a little bit. There's centrifugal pumps. These are called radial flow, mixed flow, and axial flow. Just some types of classifications. Okay. They're going to impart a force on the water. And it's usually going to be a kinetic force. The water is going to move. And then when that water moves from one portion of the pump to the other, pressure is going to be developed. And then that pressure is going to be converted to flow. All right. The most common type of pump, water treatment, wastewater collection systems, are going to be some kind of usually centrifugal pumps, whether they be radial pumps, axial flow, or mixed pumps. Okay, whether it's mixed flow, axial flow, or radial flow. Right. They can be used for anything. Raw wastewater, final effluent, return to waste activated sludge. Why? Because many times it's not that thick, right? Digestive recirculation, usually it's about 5.5%, which can be handled with a recirculation pump. Obviously, transfer pumping stations, chlorination, water injection, and mixing, nitrification, tower, influent, blah, 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 chemical feed. They're not as specifically accurate, but they can be used for chemical feed. Seal water, obviously, non-potable water, potable water, other applications involving pumping of water with indiscriminate size solids. Many of the classifications of the impellers have a lot to do with how much solids can go through these pumps. All right, there's also what are called peripheral pumps, single stage, multi-stage. Peripheral pumps, sealwater pumps. A lot of sealwater pumps are peripheral pumps. The flow, it's a dynamic flow and it's a kinetic flow, it's a motion flow. But rather than a radial, axial, or mixed flow pump, this is a pump where the flow comes in one side and goes out the other in a circular motion. And the impeller kind of looks like a miniature paddle wheel. It may look like a Frisbee with little paddles or blades on the outside. So it creates that motion around the outside casing of the pump. They could be in single stage, multi-stage pumps. There are certain special pumps and these are dynamic kinetic pumps, a jet pump, for an example. And you say, what the heck's a jet pump? Well, I'm going to tell you what a jet pump is. For sometimes with shallow domestic wells, it's not necessarily in a municipal application, but you'll get something called a jet pump, where the pump and motor is on top of the wellhead. Yes, the pump itself is on top of the wellhead, unlike a turbine pump, where there's a single motor up on top and it's a single shaft to the base, and there are bowls, centrifugal bowls mounted in stages down at the bottom of the well. It's called a turbine pump. This is a jet pump where the pump and the motor are at the top of the wellhead. All right. Now, there is a limitation on how high you can lift water to a pump. All right. And that limitation is based on the atmospheric pressure. Now, in an ideal world, I'm going to actually do the math. If you guys remember, 2.31 feet per PSI, 0.433 PSI per foot. If you take, say, 14.7 pounds per square inch, where the heck did he get that? That's the equivalent pressure of atmospheric pressure at sea level. Say you, and you take it and you multiply it by, whoops, 14.7 PSI, right? And let's see. No, you multiply. Where is it? Multiplied by 2.31. You're going to get a number. It's going to be 33.957 feet. Okay. Now, that is the absolute most in a perfect world. And I got a clue in on that, the perfect world. In an absolute perfect world, 33.957 is how high you can lift water barometrically to a pump. If you reduce the pressure in the eye of that pump to below atmospheric pressure, that's not the actual number. That's the theoretical ideal number. You're never going to be able to lift the water almost 34 feet from a pump. I don't care what a pump salesman tells you. If he says you can lift that water 40 feet, he's lying to you. He has violated the laws of physics. It's physically impossible. You can't do it. The water will not go up that high. So when you have a pump that you have to lift more than that, you got to do something about it. You got to, now this is again for a shallow domestic well, and this is a jet pump. So a portion of the discharge of that water from that pump goes back down into the well. And we haven't really talked about too much, but this fella Bernoulli, Daniel Bernoulli, he was kind of a famous scientist. He came up with this thing. He figured this out. Obviously, he didn't invent it because it was always there, but he discovered it, we shall say, right? That if you increase the velocity, and you will decrease the pressure, right? And it was applied many moons later in regards to an airplane wing. That's how an airplane wing works. An airplane wing is designed so that the velocity over the top of the wing is at a higher velocity than the velocity on the bottom of the wing. The velocity on the top, the velocity goes faster, the pressure on top of the wing drops, and the airplane has lift. Same thing applies with water, lifting water. There's such a thing called a venturi, where a restriction in a pipe will increase the velocity in that portion of a pipe. When you increase that velocity, the pressure at that throat of that venturi is going to go down. It's going to be reduced. And when I say pressure, I mean the differential pressure between the outside pressure and the interior pressure in that little venturi. So what a jet pump does, it pumps the discharge water down to the well, and then it blows that water across the venturi portion, where the well water is lifted up to that venturi section, and then it's boosted by the pressure from the jet on the venturi and brings it back up into the suction line of that pump. And so a portion of the discharge water off of the well pump is recirculated back through a venturi farther down in the well. And then it meets the suction line. And there's a reduction in pressure at that venturi section so they can increase the lift of the pump. That's called a jet pump. Now, a gas lift pump, a good example of a gas lift pump is what's called a LOX pump in the oxygen production building. Okay, it's a limited head pump. Although, wait a minute, is it a gas? No, I think, yeah, gaseous oxygen is fed through that pump. The bubbles lift it. But in say, a draft tube in a discharge, in a digester, for example, a draft tube in a discharge, in a digester. Sometimes to recirculate sludge in the digester, what they'll do is they'll recirculate some of the gas coming off the digester, and then recirculate it down into a tube and release it in an enclosed tube. Those bubbles that are being released are going to lift the sludge or the fluid up into that tube, and it's going to cause a recirculation because the bubbles are going to want to rise in the tube, and it's bringing the fluid with it. That's a gas lift pump, a low head pump. All right, so what I got here, this is a cutaway of it says here, typical non-clog vertical raw wastewater type centrifugal pump. I haven't really gotten into the construction or how it works, but basically what happens, right, that impeller turns and it's creating that force. All right, so right here, the water's getting pulled in, basically. The only way it's getting pulled in is because the pressure here at the beginning of this pump, at the eye of this impeller, which is right here, is being reduced. And the exterior pressure is pushing down and pushing the water up into that pump. Now, to fill this space, this water is being thrown out into the volute casing, which is a channel around the outside of a pump. That volute is a widening channel as it goes around towards the discharge side. The water is being thrust out there, whether it's accumulated and it's creating some pressure, and it's pressurized to the point when it finds the discharge, it goes out. So this flow that's created is creating a lower pressure at the eye of the pump. The outside pressure on the suction side is pushing the water into the pump, and then this water is being kinetically driven to the outside of the pump circularly, and it's being moved. That's how a pump works. Pumps don't suck. The outside pressure, the atmospheric pressure, pushes the water up into the pump. Okay, so there's not necessarily, because it's trying to equalize a differential in pressure. Okay, so this channel, right, this is showing the construction of a typical vertical pump, and I know there's a lot of stuff here. What I wanted to talk about, and I don't know why it's here in the presentation because I didn't really mention this. There are three, basically what are called enclosed impellers, medium impellers, open impellers. There's closed, there's semi-open, and then there's open impellers. Now, in a closed impeller pump, which is usually used for clean water, it can be used for sludge depending upon the size of the openings inside that impeller. If you have real heavy sludge with a lot of debris and maybe rags in it, you can't use a closed impeller pump because it's going to get clogged up with the crap that you're trying to put through the pump. Okay. But in a closed impeller situation, there's going to be rings, right? And this is supposed to represent the impeller. And this is the casing. So on this pump, it's showing that you have what are called wear rings. And they go around the entire casing on the suction side. They don't necessarily completely touch the impeller. There is a slight space, but there is a slight clearance. And what they're designed to do, it's maybe on the casing. This one is showing that it's not only on the casing, but it's on the impeller itself. It's supposed to close that space between the discharge side and the suction side. So like I said, the water comes up through here and is discharged out into this volute casing. On this side, it's showing it larger. All right, so this space between the impeller and the discharge is somewhat open. So what these wear rings are doing, they're preventing the water from coming back and getting repumped. It increases the efficiency of the pump. Since they're always in water, they would stay moderately cool. They're not exactly touching each other. Water does have a certain surface tension. So the clearance can be close, so it doesn't have to necessarily touch it. So that's what the wear ring's job is. All right, and this is, like I said, showing, different screws. Here's a clean out. Obviously, there's an impeller nut. There's a nut holding the impeller on with a washer. And then we move up here. And these little things that they're showing here is what's called packing rings. There's a rings of packing somewhere in here. Is it showing it? Yes, right here. It says lantern ring. Lantern ring. Packing, and I have a couple of videos on packing that I'm going to show you guys. Packing looks like braided rope. It's usually a synthetic construction. It may be impregnated with a lubricant, but it is a braided rope that fits between the shaft and what's called the stuffing box, or that clearance area between the shaft and the casing of the pump. Now, most pumps will probably have what's called a shaft sleeve because shafts are just too valuable. And these rings wrap around the shaft, and what they're designed to do is to keep water from leaking out too much from the shaft. They're to maintain a seal between the water and the world. All right. And they also prevent, depending upon how the pump operates, it may be in suction, it may be in low pressure to prevent air getting sucked into the pump too. Okay. But these rings are usually, and they're just that, they're these braided rope rings. And in the midst, dependent upon the pump, they don't all have them. There's going to be what's called a lantern ring. And the lantern ring is a spacer between so many rings of packing. And pumps are different. It could be two rings, lantern ring, and then 4 packing rings. It could be 3 and 2, 4 and 2. It depends upon the manufacturer. But there's going to be rings of packing, and then there's going to be usually what's called a lantern ring, or a seal cage is another term for it. And what it's designed to do is to be a spacer between the rings of packing. And if the pump needs what's called seal water, pumps that are usually pumping something that's really hot or something that it's abrasive, you want to have seal water. The seal water acts as a lubricant between the shaft and the packing. It keeps abrasives out. It keeps the shaft and the packing cool, because these are braided rope that's wrapped around the shaft. It's going to cause resistance to the pump. If the packing isn't too tight, it can actually smoke it. You can actually physically burn it, right? Because the friction between the shaft or the shaft sleeve and the packing can be quite intense. So it's to prevent that. It's to prevent it. Now, with a packing, you're going to have some leakage out of the pump from the stuffing box. You're going to. Maybe in drips, so many drips a minute, but you're going to have leakage. The objective is to have a little bit of leakage, but not enough that the water's blowing out of the packing. Okay, and it's designed to keep that shaft a little cool and lubricated. So the packing don't go on fire and burn it. And there's usually a shaft sleeve here, because the shafts are pretty tightly machined and balanced. You don't want to mess the shaft up too much. And then this pump is showing a bearing and a power frame. Where are they? Where are they? Oh, the jack screws are here. All right. So what this does, all right, well, let me move up the pump. So these are the packings, right? This is the packing. All right. And then this piece up here is called the packing gland. This is what keeps the packing pressed down into the stuffing box. That's what that whole assembly is called, a stuffing box. And there are 2 nuts on either side. And this is showing them as like screws. It's usually not screws. It's usually a stud with nuts on it that you tighten down. One of the keys with packing is to evenly tighten the packing, not to have it too tight. Maybe a 1/4 of a turn on each side to adjust it, so that if it's pouring out, you adjust it a 1/4 of a turn each side until it becomes a drip. And then if the studs are all the way out and you can't stop the leakage, it's time to repack the pump. Okay, sure. Okay, and then this is showing up here this is the packing gland, the packing ring. All right. Then we go up the shaft, right? This is the shaft. This is known as the power frame, which is kind of like the bearings, right? It has grease fittings. There's usually a thrust bearing or a radial bearing. They do different jobs. The thrust bearing keeps the shaft from moving in and out. In what are called split case pumps, if the shaft is horizontal, you may have opposing suction. You may have 2 impellers with an opposing, or 1 impeller with 2 suction sides. So suction's coming in both sides of the impeller. That's to prevent thrust. If you have an end suction pump, right, where the impeller is pressed against the casing and the suction comes in on one side, there's going to be thrust. The pressure reduction in that eye is going to want to make that impeller move, right? Move the shaft towards that reduction in pressure. So you may need what's called a thrust bearing. The thrust bearing keeps the shaft from moving in and out. A radial bearing keeps the shaft from moving, from wiggling from side to side. So those bearings are important. All right, thrust is in and out, radial is side to side. Fairly easy, right? All right, and then of course you have, of course, grease fittings for that, and a keyway and a shaft where it would be attached to a coupling. Now this one is showing that something that not all pumps have. This is a jack screw. There's one here, there's one here. What you do is when you tighten down on this, you're moving the power frame of the pump. You're adjusting it. And what that's actually adjusting is the wear rings, the clearance between the bottom part of the casing and this part of the pump. Not all pumps have that, but some do. It's called a jack screw. All right, so some of the key components, I mentioned the keyway. This is at the top of the shaft. Now this I got out of an old book. It's not really a hole. It's more of a, well, it is a hole, but it's more of a cutout, a little trench that's in the shaft. All right, so you have a keyway, a key set, and a key. Right. This is what connects two shaft ends together for a coupling. It removes a drilled or tapped hole, which facilitates removal of the entire pump power frame and rotating assembly without disturbing the suction and discharge piping or the pump base. Pumps are in pieces, right? Now, you usually have the casing, the power frame, which is basically the casing, the stuffing box, and the bearings. Then you got a shaft, and then you have a motor. The shaft may have bearings, or a slinger ring, if you've ever heard of a slinger ring, which is what, if water is transitioning up the shaft, the slinger ring is designed to keep water out of the bearings, and it actually flings the water off to keep water from getting into the bearings. Again, not all pumps have those as well. But this is an easier way to say it. This is a keyway. All right. It basically going to link two shafts together. So that thing is put in there, set in there, and then hammered in there, and then it's the shaft and the other part of the shaft is connected. And sometimes, most of the time, there's going to be a coupling over that. And I mentioned the jack screw, the stuffing box. Okay, this is where the packing goes. Could be a mechanical seal, but it could also be packing. All right, this is between the liquid end of the pump and the atmosphere. And there's two sealing methods. I just mentioned one, conventional packing and mechanical seals. And they both have advantages and disadvantages. This is what a stuffing box, not all stuffing boxes, but what most of them look like. So the shaft or shaft sleeve would be in the midst of this big opening, and a packing gland would probably be attached here. There may be a second, like I said, there's four places for 4 nuts and bolts. That could be for the installation of what's called a mechanical seal. So what are the advantages of conventional packing? They're cheaper. They're a lot cheaper. It's an old technology. It's cheaper. All right, they're less expensive than a mechanical seal, but they do require some maintenance. And over the long run, when considering labor and material costs and what you may or may not spill, depending upon what you're pumping, a mechanical seal may be your best advantage. But they also have another advantage, in fact, that they can tolerate a little more mechanical looseness than a mechanical seal does. Packing has a little more tolerance. Okay, mechanical seals, if you have bad bearings, you're probably going to leak. Mechanical seals are not designed to leak. If they leak, then you have a problem. And an old maintenance guy told me many years ago, if a mechanical seal is new and it's leaking, it's probably it could be the defective seal, but more than likely there's something going on with the bearings because the shaft is moving a little bit the way it's not supposed to. Anyway, okay, bad bearings, tolerances, or clearance in the stuffing box. Conventional packing has a little more give in that respect. But you are going to have to maintain them a little bit. And I have a video that, actually, I think I'll show the one on that. Well, I'll show you a video
an old maintenance video on replacing packing, and you'll see what I mean. I'll show you 3 videos in that respect, and then I have an explanation video of what packing is. So the disadvantages, again, you're putting a brake on the shaft. It's a physical braided rope around a shaft, and it could wear the shaft out. You are going to leak. It's just the way the nature it is, because of the way it lubricates. If the seal water comes from a potable water supply, then backflow prevention methods are also required. So yes, if you're going to, well, that's not really a big problem, but yes, seal water is going to be fed to the cool and lubricate the pump, the shaft, and the shaft sleeve, between the shaft sleeve and the packing. You are going to need to have some type of a backflow prevention. Most of the time in the business, it's what's called an air gap, okay, which is a big tank of water with some kind of a ball float. All right, and you may have a seal water pump that's feeding pressure to the whole system. And this ball float just opens and closes as it's needed for water. Right, and there's actually a specification to that. The air gap itself is supposed to be 2 times the diameter of the pipe that's feeding the air gap. So if you have a 2-inch pipe feeding an air gap tank, a seal water tank, the end of that water gap is supposed to be 4 inches away from the surface of the water. There is a specification. You can look it up. It's like twice the diameter of the pipe that's feeding the seal water tank. So at any rate, and I know that's a funky specification, but it is a specification, and it indeed exists. And of course, you're going to need labor, increased labor for replacement of the packing. Now, when I used to work, we would adjust the packing. This was many moons ago. So our job, we carried a little wrench, and we would quarter turn down the packing. Of course, that's not an operator's job now. It's a mechanic's job. So that has changed. Just like I used to change shear pins when I was an operator at the head end. We're not allowed to do that either now. You guys aren't allowed to do that. You have to get the whole, you have to call in everybody, the lockout, tag out stuff. We used to change shear pins at the head end. They don't let us do that. They stopped letting us do that. Probably for smart reasons, but I have all 10 of my fingers. So anyway, but yeah, you're going to have some general maintenance. You're going to have increased labor. All right, so I'm trying to remember what this video is.
Mr. Coop,
Yes, sir.
we don't adjust the packing on the Willits and filter press. Is there a reason for that, or?
Well, because it doesn't need to be adjusted.
Oh, it's just there. It's just.
Well, it does seal. Well, look,
Yeah.
move differently. It's up and down. It's not rotating.
Yeah, it's
So
true.
it'll probably last longer. We used to get buildup on the seal where we get that black, cakey, greasy looking sludge coming out. I don't know if that's still a problem.
No, I don't see that anymore, at least.
Because they used to tell us as a shift, you guys got to clean the dams because the water would be coming up. And I told, was it Johnny Duran, who was a mechanic at the time? This was many moons ago.
Oh, wow.
I said, don't fix our Willet, because the water would be coming up between the piston, and you had that little air.
Into the dam, yeah.
Yeah, and the water would flow out. And he goes, well, I'm supposed to fix it. I said, don't fix it. Because what's happening if you cut that water off, now that black cookie sludge builds up, and now we got to clean it.
and you wear the coat on the ram as well.
But he was told, oh no, they want us to adjust that so that it doesn't leak out.
No.
But I got mad and said, don't fix it.
All right.
But
Thank you.
Probably because it lasts longer, and you want that water to keep the space between it. It doesn't really leak. I have seen it where it was when the Willet went down, the sludge would blow out. So you do that, we got to fix it.
Oh, we've left it for times where sludge was shooting out the packing like nonstop, and they just let it go.
Yeah. Well, technically that's time to rebuild it.
Oh yeah, because it becomes a lot harder when all that sludge gets hard in there, and Oh, boy.
All right, groovy. So we have traveled a little bit of the same real estate. But I think
Yeah.
I think this video, actually, I'm going to show you something else after I show you this. I think this is the video where they're changing the packing. He's installing packing on a brand new pump. There's some mistakes, but this is how they do it where they work. I will qualify it because I'm trying to remember how many rings of packing he's putting in, because there are rules. For example, if like say you have 4 rings of packing, and then you have a lantern ring, and then you have 2 rings of packing. If you have 4 or more packing rings, and I'll show this video and then another one, and you'll understand what the splits mean. Those splits are supposed to be 90 degrees apart. That's actually a test question, usually in the C and possibly S, maybe in the W and the T if there's mechanical, if there's braided packing. But 4 are supposed, if you have 4 or more rings of packing, the splits are supposed to be set 90 degrees apart. If you have 3, they're supposed to be set, and I know this is weird, 120 degrees apart. There's 2, the splits are supposed to be 180 degrees apart. I know. Let me show you guys this. This is a guy building it in a factory. I just thought it would, because if you've never seen packing, oh, wait a minute. I thought I was gonna, and then I got another video I want to show you. I think this is the one. Yeah, this is the one. So he makes some mistakes here, and then I'll show you another video.
Okay,
Actually, excuse me a minute, I have to.
811
You guys watch this.
It's a 4x3x13 medium frame, duct iron construction. Today we're going to be showing you how to install a packing plan, and I have Wayne take it from here.
Okay, the first thing we want to do is we want to put our studs in the stuffing box. We run them down by hand first, so not to cross thread. Stud driver. Stud, yeah. You only actually need 2 studs, but for purposes in the future, if they want to change it over to a different gland or chemical seal or any other type of seal they want to put in, they already have this installed. 2 we're not using. I'm going to put the nuts on. And run them all the way down. Okay, that'll clear the steel. Now we take our sleeve and put it face propeller side down into the stuffing box. And let it sit there. Then we take our first piece of packing, and we'll be putting in.
I know that you don't like to eat it. You said your class was gonna finish at 7:30. I'm gonna go focus on class and I'll take it.
All the way down into the
It's better.
Then we get another piece. So you want to go opposite. The way we had the first time is this way. This way. This time you want to put the second piece in opposite. Push it all the way to the bottom.
Sorry.
Packing pieces in there. The next thing we want to do is we have this lantern ring. But this allows fluid to be passed into the gland to keep it cool. And they're split. They have an opening.
Can you stop those onions?
4 corners of it.
I'm like Mexico Deli.
All they're gonna go in. They're gonna go in together, and they're gonna look like that inside.
Can we freeze cheese?
You want to keep splits opposite of each other again. The first one I put in, I'll take this opening, and I want to put it right next to
Okay.
that's for the cooling.
Right? That was cilantro and the
Next
cilantro.
one on top of it.
So
We were
This way,
cross on yesterday. You were with me.
but lining up the 2 openings.
yesterday.
Push that.
We're gonna put the seasoning stuff here, the onion,
Go back and
garlic, the
on the bottom.
Yes.
Again,
Who's there? Why don't you finish what you need to do, like you said you would?
Make sure your book doesn't catch on fire.
number 2. I'm using a punch to push it down. No more damage to the package. The last one's gonna go opposite.
What are you looking for?
Put on. There is a way to put it. There's a long neck here, a short neck here. The long neck goes towards the pack. That'll pull that packing in. Flip it over. Just like that. Two nuts go on. And you want to keep this loose. You do not want to tighten it. That way it goes on the puff easy, and this gets tightened as you roll it with the hood. Okay? More guide pins. Put on the stuffing box.
Yeah, it is choppy. They're all gonna be that way, I'm sorry. But I wanted to give you guys a visualization. Actually, let me stop it here. All right, now an interesting, like, yeah, Christian, it is choppy, but when you look at this, now there's a few things I'll say it now. This is not how you would do it in real life, right? Because this is on a bench in a factory and everything's nice and clean and good. You ain't got that luxury when you're doing packing. Now, obviously, this is how they do their packing at their factory, which is fine. But I mentioned the rules. I don't want anybody to be deceived. There are guidelines when you're replacing packing. You're supposed to, like I said, where those splits are, like he was putting them all opposite each other. And hey, you know what? It was a 3 and 2, not necessarily a big deal. But the rules say if there's 4 rings, they're supposed to be 90 degrees apart. So if you have 4 packing rings, say before the 4 rings, seal cage or lantern ring, and then 2. All right, so those 4 packings, when you put those splits in, they're supposed to be 90 degrees apart. So the first one would be at 12 o'clock, then 3 o'clock, then 6 o'clock, then 9 o'clock. They had pre-cut packings. It didn't seem like his angles were really good. They're supposed to kind of match each other. But like I said, this is how they do it. So what I'm going to do is I have another video that I want to share with you guys. It's about 15 minutes. It's looks like it's from the 60s or the 70s. And it's actually pretty good. I think it's pretty good, but it's for information, not entertainment, because I want to get that clear. But anyway, this guy takes this video, he takes it and slides it on the pump. And it's the rest is history. He did say some things that were right. What's important with packing is that the seal cage, and I call it the seal cage from time to time, it's a synonym for lantern ring. The lantern ring and the seal cage, the lantern ring has to line up with the seal water inlets. That's one of the most important things. If you have seal water going to your pump, that spacer, that lantern ring has to line up with the inlet to the water, because you need a space for that water to get in between the shaft or the shaft sleeve and the packing rings, okay? And what he also said about hand tightening them, a lot of places will recommend to tighten them down and then back them off a little bit, so that they're somewhat hand tight when you first put it in. Because when you start a pump with new packing, you're going to adjust it as it's running, okay? So let me see if I can call this up here. Wait a minute. I'm going to show you another choppy video. I'm trying to think which one I should show you. I have two of them. I got this guy here. Actually, maybe I'll show them to you both. This is like from the 60s or the 70s. You can tell the sideburns and the groovy mustached here. But anyway, no, there's information here that is actually appropriate. And he's talking about another video that they did with valves, and it's going to be choppy again. But this is more like real life application.
Workman is then ready to begin dismantling
So
the seal on the inboard.
This happens more than you know. You guys that are working
As I
pumps,
said,
you
the
know.
steps involved here
You ain't got no
are
room.
the same as those for a valve. First, the two nuts which hold the gland follower in place must be removed.
Gland follower is the same as the packing gland.
Now you notice something peculiar to pumps here. You're frequently working in an environment where you have limited access to the parts that you need to work on.
I don't know how many of you have
Notice in this example,
ever changed
the
packing
bearing
on a
is so
pump.
close to the seal area that there's really a quite limited space to work in. And this is one of the problems that you're going to be faced with when repacking pumps. So the first step the workman performs then is to loosen and remove the two nuts which hold the gland follower.
I'm watching to see if it freezes up.
Once these nuts have been taken off and set aside, then the gland follower can be pulled back on the shaft. Now again, you'll notice that he has a limited space to work in. With some pump designs, the gland follower is in two pieces, and in that case, once it's been unbolted, the two halves can be taken off of the shaft and set aside, giving more room. This particular pump, the gland follower is of a one-piece design, so it's simply drawn back as far as possible on the shaft to allow packing removal.
Now, if you see what he's doing, he's
The
screwing
packing
that
is
packing
removed
tool
in
in
exactly
there
the
to
same
catch the
fashion as we
packing and
discussed
then
for valves.
slowly pulls it out.
Using a packing hook or some similar tool to thread into the packing, it can be drawn out of the stuffing box. And as before, care must be exercised with whatever tool you're using to be certain that you do not scratch the surface of the shaft or the packing sleeve, which is frequently installed on the shaft, and the surface of the stuffing box itself. So the workman continues to repeat these steps to remove each ring of packing. He makes use, in this case, of a corkscrew-like packing removal tool, threads it into the packing until he can draw out at least one end of the ring and grasp it by hand and remove it. Now in this particular pump, after removing the first two rings of packing, the workman saw that the next component in the stuffing box was a lantern ring. So he made a note on the data sheet that he kept for this particular job that there were two rings of packing installed on the outside of the lantern ring. After making this note, he was then ready to remove the lantern ring itself. The lantern rings are normally provided with holes, which can be engaged by a packing tool in order to allow removal of the ring. In some cases, you'll find that the holes are tapped If that's the case, then a piece of threaded rod or a long bolt can be used. It can be threaded into the hole, and then you can use that to draw the lantern ring out. In this particular case, because the lantern ring had holes, they were not threaded. So instead, the workman makes use of a packing tool, engaging it in the openings of the lantern ring in order to draw it out of the stuffing box. Now, as you can see, frequently this takes a certain amount of grappling in order to get a hold of the lantern ring, because of course it's not flexible like the packing is. In this particular pump, the lantern ring is of a two-piece design. So what comes out of the stuffing box is really half of the lantern ring first. So after working around with the packing tool, his fingers and so forth, to work it free, half of the lantern ring can be drawn out of the stuffing box and set aside. And this, of course, is followed by the second half. As before, when removing a lantern ring, use care to avoid scratching either the stuffing box walls or the surface of the shaft or packing sleeve as appropriate. Now, once the two-piece lantern ring has been removed from the stuffing box and set aside in a safe location, the workman then proceeds to remove the remaining packing in the stuffing box. This is done as before using a packing removal tool, using care to avoid damage to the shaft or the stuffing box walls. He threads the tool into the end of the ring of packing, and then using the tool draws that free end out of the stuffing box to where he can get a hold of it, and then removes the ring itself from the stuffing box. So he continues to remove packing in this manner until all of the packing has been taken out of the stuffing box. After removing the last ring of packing from the stuffing box, as with the valves that we discussed earlier, the workman will then make notes regarding the number of rings of packing which he has removed, and this information will be used in determining how many he needs to reinstall. In the case of this particular pump, there was a total of 6 packing rings. The stuffing box contained 4 rings, followed by the lantern ring, followed by 2 more rings of packing. So after making these notes, the workman then proceeds with the next step in the operation. And again, this is a predictable step after what we've discussed earlier with repacking valves. He needs to clean out the stuffing box and the surface of the packing sleeve on the pump shaft. Now again, you'll note that he has difficulties because of limited access to the parts that he's working with. However, it's important that the cleaning be performed as best you can. The purpose is the same as we talked about earlier, to remove any remaining bits or pieces of packing which may have flaked off during the packing removal process. So after wiping out the stuffing box with a rag, he is then ready for the next step. And again, this is one you could probably predict: a careful inspection of the stuffing box and the surface of the shaft to look for any nicks, scratches, or gouges, which might result in excessive leak-off even with new packing installed. And of course, following this examination, he's then ready to make whatever checks he needs to determine the type and quantity of packing he will need to install when repacking the pump. Now, how does he determine what type and size of packing he should use in the pump? Well, he does it in exactly the same manner as we've already discussed for valve before.
Now, we didn't watch the one for valve packing, so I'm
You
just
may
gonna,
refer to the measurements that we discussed with valves.
I'm gonna
You
move
would
along.
measure the inside diameter of the stuffing box
All right,
and the outside diameter of the shaft or packing sleeve. And then from these measurements could calculate the size of the packing required. If necessary, he may also measure the depth of the stuffing box to determine the number of rings of packing that were required. Well, in any event, the steps are essentially the same as we've discussed earlier. So while our workman is making these determinations and obtaining the new packing, why don't we take a break and let you review the steps we've discussed in removing pump packing.
now obviously this is some kind of a training video. I don't care, it's giving you guys a visualization.
On the last segment, we saw the steps involved in removing packing from a typical centrifugal pump. And if you recall, when we left, the workman involved was determining the type of packing that he was going to need to install, and he was on his way to get that packing. Well, he's now obtained the pump packing, and he's ready to cut it into rings of the appropriate size. So let's join him and see how he does it.
And this next part was where I kind of
Now,
wanted
as
to
you
get into
probably
it.
noticed, because of the tight space that he had to work
Because you'll
in,
see this in the
it
book,
was not
but it doesn't give you a
practical for the workman to
visualization.
wrap
You'll
the
read about
packing
this in the
around
book.
pump shaft in order to establish rings of the proper length.
Now, a lot of
So
times,
instead,
like you
what
said,
did
he
was
may
to
mention
obtain a
it in the
piece of
book.
pipe
The
which had the
maintenance
same
O&M
outside
manuals
diameter as the
usually
outside
tell
diameter
you
of the pump
what
shaft.
kind of packing, or
And he is now wrapping the packing around that pipe. And
you
will
may
cut
get
the
pre-cut
rings
pieces
in this
too.
manner.
So
Now, this does give one advantage over using the shaft itself. There's now no concern about performing the cutting while the packing is wrapped around the pipe. Now, you recall when we used this technique on a valve, we were using the valve stem, and he could not cut all the way through the packing for fear of scarring or scratching the valve stem. But since he's using a piece of pipe, he can perform the cutting while the packing is wrapped around the pipe, thus assuring himself that the packing is cut at the proper angle and that the rings will fit as they should into the pump. So he continues to cut the packing one ring at a time until the required number of rings have been cut. And you recall, for this particular application, a total of 6 rings were needed. Once the new packing has been obtained and cut into rings of the proper length, it is then installed, following the same steps that we discussed for valves. So the workman takes the first ring of packing, places it around the shaft, verifies that the ends join as they should, and then presses it into the stuffing box. Now, as with valves, it's important that each ring of packing be individually seated in the stuffing box. So first, he pushes the ring in as far as possible with the gland follower, and then seats it using a special tool which he has made. This is a flexible packing removal tool with the hook cut off. Now, the reason he uses this is because of the tight quarters involved. It's impossible to use a bushing of the type that we saw earlier on this particular pump. Now, of course, it's important that you not use a pointed object because that could damage the new packing. He then repeats this step with each succeeding ring of packing. And since there are 4 rings installed before the lantern ring, he staggers the joints 90 degrees, following the rule that you will find in your workbook. Now, after a total of 4 rings of packing have been installed, he is then ready to install the lantern ring. Now, it's extremely important where lantern rings are used that they be set in position at the proper point in the sequence, because the lantern ring must be positioned in the stuffing box such that it matches the connection for lubricant or sealant as appropriate. In this particular case, water is injected as a sealing medium on this pump. But regardless of the reason for the lantern ring, it's extremely important that it be installed at the proper point, which, as you'll recall in this pump, is after the 4th ring of packing. So the workman takes the 2-piece lantern ring and inserts it in the stuffing box, using care to be certain that the 2 pieces line up properly, and then fully inserts it against the 4th ring of packing. Next then comes the remaining 2 rings of packing, which are installed after the lantern ring. These are installed in the same manner as we've just seen. Now, since there's only 2 rings at this point, that is 2 rings after the lantern ring, as we're going to see, the joints of the 2 rings are staggered 180 degrees, again following the rule you'll find in your workbook. So the workman installs the first of these 2 rings. As before, wrapping it around the shaft, carefully assuring himself that the 2 ends butt together as they should, and then seats the ring by the use of the gland follower. Since the stuffing box is almost full at this point, it's no longer necessary for him to use that special tool in order to assure that the ring is firmly seated. Instead, he can take the gland follower and press the ring into position by hand. This is also point 180 degrees from the ring is installed, of course, then the gland follower will come along behind. So the workman takes the ring and presses it into the stuffing box by hand. Then, with it in position, the gland follower is drawn up into its position and placed over the studs which hold it in place. Then the nuts are threaded onto the studs in preparation for an initial tightening of the packing. Now, it's very important that this packing receive only an initial tightening at this point. As with a valve, the final tightening is done with fluid in the pump and the pump in operation. Over-tightening at this point can result in overheating and destruction of the packing when the pump is started. So instead, it's just drawn up snugly and evenly, and then the two nuts are backed off again and left finger tight until the pump can be placed in operation. So those are the steps involved then in installing packing on a typical pump. And the one final step that we have not yet seen is the adjustment of that packing. We said that needed to be done with fluid in the pump.
All right, I'm going to call it quits here for this one. Because I don't think it's necessary. You guys know you have to adjust the packing. All right, usually it's a quarter of a turn at a shot. And it's tighten it, and it has to be even. It has to be even. And maybe I'll save this one for another time. Because this guy, it's about 9.5 minutes, and he talks about compression packing. Actually, he shows a split case pump here, so maybe I'll play this one next.
Video blog, and today I'd like to talk to you a little bit about compression packing.
What he's showing us was called a split case pump. I don't know where you guys have any anymore. Got a nice cutaway.
Anytime a shaft penetrates a fluid-containing chamber, a leak path is created. Let's take this pump, for example. It's driven by a motor and it's supported by bearings on the outside of the fluid chamber. But the impeller driven by the shaft has to be submerged in the fluid inside of the chamber in order to pump that fluid. That means that the shaft is going to have to enter the chamber in two places, here and here. Now, unless you want to flood the room and empty the piping system, those holes are going to need to be sealed, but they have to be sealed in such a way that the shaft can still spin freely with minimal friction. Now, there are two generally accepted devices used to accomplish this task: mechanical seals and compression packing. Mechanical seals use two very flat and highly polished surfaces to create a gap so tiny that not even a single droplet of fluid can squeeze through. Compression packing, on the other hand, is pretty low tech. It's essentially just rope that's stuffed around the shaft and then compressed tightly to prevent excessive leakage. As we'll see in a moment, compression packing leaks constantly, it damages shafts, and it requires frequent adjustment and replacement. For these reasons, it's been supplanted by mechanical seals in most applications since the proliferation of mechanical seals in the 1950s. But because of the relatively low upfront costs of compression packing, it is still in use. In this video, we'll cover the basics and selection of compression packing, and we'll leave replacement procedures for a follow-up video. Compression packing is an ancient technology. As far back as 5,000 years ago, sailors were faced with a common problem. Boats and ships often have a rudder or a fixed pivoting oar at the rear of the vessel for steering. The rudder is connected by a shaft to a control handle called a tiller on the deck. If the rudder shaft penetrates the hull of the vessel below the waterline, then water can leak into the bilge. So ancient sailors solved this problem by taking old pieces of clothing, sailcloth, rope, and anything else they could get their hands on, covering it with animal fat or wax, and packing it into the gap around the shaft. Eventually, little box-shaped housings were constructed around the shaft, and a gland was installed which could tighten down against the packing material, compressing it and improving the seal. Thus, compression packing, the stuffing box, and the packing gland were born. As we can see in our example pump, this basic sealing mechanism has remained relatively unchanged for millennia. However, there have been some improvements in packing construction and materials. The compression packing available today typically has a square cross-section and is sold in standard sizes as individual pre-cut rings or in bulk quantities in large coils. There are multiple types of construction, including metal foil packing, for applications where other types of packing would be too soft and would tend to extrude out of the stuffing box. But the dominant type of packing has a braided fabric construction. Material options range from plant fibers, animal fibers, and mineral fibers to synthetic plastics and even metals. Flax is a plant fiber that's been the industry standard for many, many years. It's cheap, readily available, and it offers good sealing for general purpose applications. Synthetic aramid fibers like DuPont's Kevlar are even more abrasion resistant, and they can handle higher temperatures and shaft speeds. Another common plastic is polytetrafluoroethylene, more commonly abbreviated as PTFE, or known by its trade name, Teflon. It has very good lubricity and excellent chemical resistance. Because it's non-reactive, it's often used in applications where process fluid contamination is completely unacceptable, like in the food industry. To help reduce heat generated from contact with the rotating shaft, this bulk fiber material is impregnated with some kind of a lubricant, like oil, grease, wax, graphite, or various synthetics. In the last 30 years, industry has embraced a mixture of PTFE and graphite impregnated with a high-temperature lubricant that often goes by the trade name GFO. Now, although there's no one-size-fits-all packing solution, this material is about as close as it gets. It has a very wide range of applications and it boasts a very long life, but the trade-off is that it's ridiculously expensive. The many options for bulk fiber material and lubricant offer up an almost infinite number of combinations. In the end, packing selection comes down to operating temperature, sealing pressure, shaft speed, and chemical compatibility with the process fluid. But you should really ask your local vendor to determine which specific type of packing is right for your application. Because of the way that it forms a seal, compression packing has to grip the shaft tightly during operation, and this inevitably leads to all types of problems. Compression packing generates a lot of friction, and that puts strain on motors and produces large amounts of heat, which must be dissipated. Maybe you've noticed that I've been saying that packing prevents excessive leakage, not that it prevents leakage entirely. That's because packing has to leak a little bit during operation. In an application where there's infrequent movement of the shaft, then the packing can be fully compressed to stop leakage entirely. Take this gate valve, for example. Actually, this one uses O-rings, but many gate valves do use compression packing to seal around the stem that raises and lowers the gate. But in reciprocating or rotating machines like our pump, some amount of leakage is necessary to lubricate and cool the packing. For non-synthetic materials, the leakage rate is about 15 drops per minute, and synthetic materials require a little more leakage, around 30 drops per minute. This persistent leakage is one of the unavoidable pitfalls of using packing as a seal, but without it, the packing would quickly burn up and stop sealing altogether. In order to further improve lubrication or to flush away abrasive grit and dirt, an external flushing line can be plumbed to the stuffing box. Now, usually this is just the process fluid plumbed directly from the fluid chamber, but if the process fluid is too abrasive or chemically incompatible to be used as a flushing fluid, an external fluid source can be used. It's usually water and it's pumped directly to the stuffing box. Now, external flushing lines typically go hand in hand with devices called lantern rings. A lantern ring is a metal or plastic ring with grooves and holes in it that's installed in the stuffing box in place of a ring of packing. Its job is to redirect the flushing fluid throughout the stuffing box, and therefore it should be installed so that it's in alignment with the flushing line port. Another unavoidable pitfall of using compression packing is the damage done by abrasive particles grinding against the shaft. Now, these particles can come from the packing, from the process fluid, or somewhat surprisingly, from the shaft itself. You see, metals corrode to form oxides on their surfaces, whether it's iron oxide from steel, chromium oxide from stainless steel, copper oxide from bronze, or aluminum oxide from aluminum alloys. These oxides are extremely hard and abrasive. It's the same stuff used in abrasive grinding wheels. Contact between the shaft and packing causes the oxides on the surface of the shaft to embed themselves in the packing rings, which then grind grooves into the shaft. Eventually, the shaft will be so worn down that it'll have to be replaced. One way of dealing with this is to use a sacrificial sleeve, which fits over the shaft and can be easily replaced when it wears down without having to replace the entire shaft. Perhaps the most frustrating thing about compression packing is that it needs to be adjusted periodically. During operation, lubricant squeezes out of the packing and the packing wears, which causes the leakage rate to exceed the minimum required for lubrication and cooling. So maintenance staff must regularly inspect the seal for excessive leakage and tighten the packing gland if necessary. When tightening the packing gland no longer effectively controls the leakage rate, then all the lubricant has been squeezed out and the packing needs to be replaced. Well, that's your introduction to compression packing, its function, its origins, its construction, and some of the considerations for its application. And that's it for today from the Machine Tech video blog. I hope you learned something.
All right, cool. So I don't know if you guys, this guy I've actually seen a few of his videos. I kind of like it, the way he explains things. The other one was an old training video. I don't know what year it was from, but between the sideburns and the hey, what's going on here? And this guy will just put this to the end. But I wanted to show that. And then, oh, what's going on here? Let's do this again. All right, so where are we at? All right, so let's do this. Okay. Okay, so he mentioned mechanical seals. They have some advantages. Like we usually think of seals as packing or mechanical seals. They do the same thing. They do it differently, but they do the same thing. A lot of pumps today, of course, have mechanical seals. And it's kind of like for the same reason that he said, like, because there's going to be leakage. Usually they're a lot more expensive to put in up front. But there's basically, if they're in and they're good, they're going to stay there almost forever. When they're adjusted properly, when they're put in, again, they're going to be pretty much maintenance free. And there's no adjustment like with packing. All right, there is no leaking. If you have mechanical seals that leak, they're not doing their job. Mechanical seals are not supposed to be leaking. Okay, it means that either there's something happened with the seal, something in the seal is defective, but most times it means that something has made that valve, that shaft or shaft sleeve wiggle a little bit more than it's supposed to. There's no leakage. Like he said, what did he say? 15, 30 drops a minute. It used to be, yeah, like a drop a second or something like that. And it's drip, 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 drip. If you see that, then you're good with packing. If it's flowing out, then maybe you want to take it down a quarter of a turn and see if that stops it or slows it down. Don't take it down too much. If you do, then back off the other way. Now that's usually a maintenance guy's job. It's not necessarily an operator's job, but it used to be. The operators used to be able to adjust the packing when they were expected to. They stopped doing that like in the early 80s where they said, no, they don't want operators to be adjusting the packing. But at any rate, there's no leakage out of the stuffing box like there is with packing as far as mechanical sleeve. And there's also less wear on the shaft. Like he showed that video in the last video I showed you with the cutting in the grooves. You won't have that with a mechanical seal because one piece is actually attached to the sleeve. The other patch is attached into the stuffing box. There's a rotating assembly and a stationary assembly. Some places will have multiple seals on a pump. The only wear it happens between the seal faces. All right, and there's obviously less power consumption because they're more efficient. When installed and operated properly, they're going to last for several years before replacement is necessary. So now the disadvantages, there really aren't that many, but there's one. It's a lot more expensive initially. That's pretty much it. It's a lot more expensive. Once an operator or once a mechanic, we'll say, a maintenance technician, whatever title you want to put on it, but there's going to be more training to put a seal in, mechanical seal, than it is for packing. You know, you're just stuffing rope in a box, right? But with you're going to require a few more a few more techniques. And if you have mechanical seals, you're probably going to have a manufacturer come in for the first time and show you guys how to do it and to do it right. And this is, I think this is Garlock, this video is from. Again, it's another commercial, but give you an idea. It's their particular brand of mechanical seal.
Pipe leakage, a natural occurrence found in all types of industry today. If not controlled, it creates costly problems that affect you directly. Problems of pollution, a potentially destructive force affecting the environment inside and outside your plant. Corrosion and bearing fatigue, devastating factors destroying equipment and reducing efficiency. Product loss, increasing costs and decreasing profits. Maintenance requirements, resulting in wasted inventory and the inefficient use of labor. Leakage, slowly eating away at your business productivity. Many industries today attempt to control leakage by using braided packing. Where packing may be ideal in some situations, it is not in others. Since packing must leak in order to work effectively, it is not recommended for use in industries that follow strict environmental regulations, such as chemical, food processing, pharmaceutical, petrochemical. Here, leakage-related results such as pollution, corrosion, and loss of product cannot be tolerated. But Garlock, the industry leader in sealing products, realizes this and responds with mechanical seals, the solution to these problems and more. Mechanical seals uniquely designed to eliminate leakage, offering convenience and cost-saving benefits in many areas. Mechanical seals cut down on pollution, ensure worker safety, reduce maintenance and house cleaning costs, and stop valuable product from going down the drain. But the benefits don't stop there. Mechanical seals dramatically improve the life of bearings. Mechanical seals create less friction, increasing shaft and sleeve life by eliminating wear associated with braided packing. And mechanical seals reduce product dilution, saving you money. To realize all of their benefits, let's take a closer look at how a mechanical seal operates. Contrary to popular belief, mechanical seal design and operation is relatively simple. Basically, it consists of two flat faces, one stationary, mounted in the gland, and one rotating with the shaft in a circular motion. Next, spring pressure is incorporated to help hold the faces together. This spring pressure also serves to compensate for end play and some shaft runout. Finally, secondary sealing elements are added to prevent leakage along the shaft and around the stationary face. These secondary sealing elements meet a wide variety of applications and are available in several styles and materials. Now, the seal design is complete, an assembly that stops leakage in the three critical areas. Have seal faces, at the face of the stuffing box, and under the seal along the shaft. During mechanical seal operation, fluid pressure inside the stuffing box forces the two sealing faces closer together, while providing the faces with a lubricating film, reducing frictional wear across the faces. This minute amount of fluid would be considered leakage. However, the frictional heat generated by the faces causes the fluid to evaporate. Now that you have a basic understanding of the seal operation, let's talk about the seal types. Mechanical seals fall into three distinct categories: inside or outside single-mounted seals, double seals, and cartridge seals. Inside or outside single-mounted is determined by the position of the rotary portion of the seal assembly. With inside seals, the rotating assembly is mounted in the stuffing box of the pump and is completely surrounded by the fluid it seals. This fluid helps to cool the mating faces. The fluid's hydraulic force keeps the faces in contact. And solids in the fluid are thrown away from the faces by the centrifugal force. Outside seals are normally used when the material being pumped is corrosive or detrimental to the entire seal assembly. By locating the seal outside of the stuffing box, all corrosion-prone elements of the assembly are exposed only to the atmosphere. And because the entire rotary assembly is readily accessible, it's easy to install, inspect, and maintain. Outside-mounted seals are also ideal for non-metallic pumps because together they offer superior corrosion resistance. The second category, double seals, are recommended when the fluid being pumped is a poor lubricant, abrasive, or a combination of both. A double seal, consisting of an inboard and outboard assembly, allows the introduction of a pressurized, clean lubricating fluid, thereby isolating the product in the stuffing box and the injected fluid in the stuffing box from the atmosphere. Because of this ability to isolate, double seals are also recommended for surfaces that are toxic, flammable, or detrimental to the environment. The third category, cartridge seals, combines all components into a preset assembly that is easy to install. This eliminates the need for time-consuming complicated measurements and handling. All cartridge seals come in either single or double versions and are often the most economical choice when converting from packing to a mechanical seal. In order to meet a wide variety of applications, each of these three distinct seal categories are available in unbalanced or balanced designs. An unbalanced seal allows all of the fluid pressure in the stuffing box to act as a closing force on the faces. This particular design is most effective in low-pressure applications. For high-pressure applications, however, a balanced seal is required. Here, a change in the face configuration allows some of the fluid pressure to be redirected, offsetting the total closing force on the faces. This reduction generates less heat and normally extends the seal life. Garlock, the leader in providing quality sealing products for the past 100 years, offers an in-depth line of cost-effective mechanical seals. Mechanical seals that are specifically...
All right, so that's mechanical seals. Again, they're not supposed to leak, require a little bit more effort to be put in, a little more training, but they last longer. So cost effectiveness, either or. Most places would put seals in. I remember the HTPSR pumps, for an example. When that pump station was first installed, those seals were really expensive. They were a couple of $1,000s. I can't remember the exact number. And when that station was first installed, initially they said, oh, you won't need seal water. Okay, fine. Stuff, the decant, the Supernate, the HTPSR was pH about 4.5, 120 degrees, and it had some abrasives in it. You don't need seal water. Okay, fine. So we blew through those seals easy enough. Then they came back and they said, well, we'll recirculate. We'll recirculate the stuff from the discharge side to the pump and use that as seal water. We'll put these new seals in and it'll be fine. Okay, fine. We blew through those seals too. Now this, mind you, this was on their dime. I think it was Chesterton. I'm trying to remember the contractor. I can't remember who built the station. But at any rate, I know like John Rotolo was involved with that, with the engineering, and he was kind of like, these guys got to get it right. Anyway, then they finally said, okay, we need seal water. So remember, it was John Gallucci was in charge of the pipe shop. Him and his guys, they put the pumping station, Frank Fazzini, I'm trying to remember who else was on the job. They built the seal water system. They tapped it off the seal water for the decant pumps and installed the seal water system. And then we got the new seals. Okay, we're back in business. Last I heard, that was it. They never had to replace those seals again. I don't know, maybe that's changed over the last couple of years, but that was the way that went. And there were little flow meters for the seal water, so we knew that they were actually getting the flow. So they installed seals. Took them a couple of shots, but they said, yeah, no, guys are right. Because the stuff, the Supernate, like I said, it was hot. It's like 100 and some degrees, 120 degrees, if you will. pH is about 4.5. And because the decant was not settling like it's supposed to, it was real abrasive. I don't think they accounted for the amount of solids that were in the supernatant. I can't, well, where that solids came from, I have my own opinions, but that's been long gone. I'm not there anymore. So anyway, some of the points, some of the parts of the key components, we talked about the packing, I talked about the seals. They do the same thing, they just do it slightly differently. One of the big components, I mentioned the keyway, which is where the two shafts are basically attached to each other, and then there's usually a coupling on top of it. Next is the shaft itself. The shaft is a finely tooled, balanced piece of steel, tool steel. It's not like a disposable part. I mean, yeah, it is, but they cost a lot of money. They have to be balanced. So it's not like, oh, you just put an extra shaft in the that's why it has to be protected as much as it does. That's why you usually have shaft sleeves. And like he said in the video, to keep grooves from being cut into the shaft. This is what the book referred to this, the older book said, the spinal cord of the pump's skeletal system, which is pretty accurate. Yeah, it's got to be straight, it's got to be balanced, it's got to be true. You know, it is expensive. It needs to be handled very carefully during assembly, and like if you're doing packing, you got to make sure you don't ding it in any way, because you don't want to have damage. It has to be in balance. All right, the other part that's really most important is the heart of the pump, which is the impeller. Like your valves in your heart reciprocate and move the blood around, the impeller is what's moving the fluid around in your system. And this is the heart of the pump, is the impeller. The spinning force of the impeller causes the centrifugal force, which then pumps the water. These, I mentioned this before. Okay, you'll hear some terminology. Open impeller, semi-open impeller, closed impeller. Now, maybe these pictures are not that accurate. I tried to find some that were. But anyway, what this is showing us here, an open impeller is just that. It's basically the impeller in the casing. I mean, there is a backing, but that's for stability of the impeller, right? As opposed to a semi-open impeller, because I know the line's a little sketchy between open and semi-open. This is a semi-open impeller. The impeller vanes are here, and the difference is what's called a shroud. So there is a backplate on this impeller that encloses all of the impeller vanes from the back end. What's the difference? Who cares? Okay, so the reasoning, this open impeller, the vanes are wide open, they're out there. And the reason for that is they can pump heavy solids, larger solids. And they're designed that way. There's a form of an open impeller, and you may hear the term, it's going to be called either a vortex pump or a torque flow pump. Those pumps, I can picture them right now. All right, there used to be a bunch of them. There's less now than there was a couple years ago at PVSC. The thickener pumps, the thickeners, the pumps that pump from the sludge wet well up to the grit cyclones are what are called torque flow pumps. You may refer to them as Wemco pumps. Okay, those are open impellers. They're not quite designed the same as this, but they're open impellers. Okay, those pumps, the impeller sits back in the casing. So as that impeller spins, it's still creating that kinetic energy and it's still creating that differential pressure. But it's almost supposed to be as if, I don't know if anybody's ever been in the lab, when you put a stirring rod on a magnetic stirrer inside of a beaker full of water. It sits down there and it starts spinning at the bottom of the glass. And what you see in the glass was the water's being stirred. The side parts, the outside of that water glass, the water level goes up. And the center portion of that water in the glass goes down. All right, that's what happens in a torque flow pump. That's what happens in a vortex pump. You're creating a vortex. You're increasing the pressure around the outside by creating that kinetic energy, and that pressure is increasing. And in turn, what's happening in the middle, the pressure of the fluid is at the center of that vortex is going down. So atmospheric pressure is pushing on it, and that level's going down. A vortex impeller kind of works that way. It's like a stirrer at the back of the casing. And as it's stirring that water, it's creating a drop in pressure at the suction, at the eye portion, the suction of the pump, and the pressure around the outside is increasing. And if that's increasing, it's finding a channel through the discharge side of the pump. It's creating that vortex. Those pumps pump a lot. They are very large flow style pumps, and they can pump a good measurement of solids. And the exposure velocity wise directly from the impeller to whatever you're pumping isn't as great. So if there's abrasives, most of those abrasives are going to get thrown out before it reaches the point where it's going to impede on the impeller and deteriorate it. And it's called a vortex pump. They are open impeller pumps. Okay, and they exist, primary sludge pumps and the primary clarifiers, the thickeners, the sludge pumps, primary sludge pumps and the thickeners. I'm trying to think where else. They used to be in storage. They were replaced with progressive cavity pumps. Actually, that happened before I retired. But we used to have two big Hawken Lemco pumps down there with the two progressive cavity pumps in the middle. I'm trying to think where else. I don't think they're there anymore. The sludge recirculation pumps in the filter press, there used to be two of them in the alcove there. They used to be, I don't know if they might have taken them out some years ago, I don't know, but those
we took them out, Mr. Coop.
Okay, because those are.
We plan to replace them.
Oh yeah, with the same style?
I'm not sure what style yet, but yeah, the recirc pumps are out.
It's interesting. I remember when the impellers, one of the impellers fell off of one of the pumps.
No way, really?
Yeah.
Oh yeah. Boy.
The pump was running, the motor says, wow, this looks pretty cool, but it's not doing anything. And the impeller, and it wasn't supposed to happen, but it did. And that shows you the amount of clearance between the impeller and the casing. The impeller walked off the edge of the shaft and dropped into the casing. So the pump was running, but it was like, it's not doing anything. It sounded real quiet, but it wasn't moving anything. But yeah, those pumps, I know they were abandoned for more than a few years because they weren't really effective. But those same style of pumps. Those motors are huge for what they have to move. And that's because they pump a lot of heavy solids. But those are considered open impeller pumps. So like I said, the next pump is a semi-open impeller, which is the vanes are visible, but there's a shroud behind them. And I mean, I know like the line is drawn, it's a little bit gray between an open impeller and a semi-open impeller, but for the for the rules of definition, they're for medium-sized solids. And they're also not as efficient as the one on the right, which is a closed impeller, where there's two shrouds. That's what they're called. The impeller vanes are enclosed in two shrouds. Then the one on the right are most efficient. That's usually for clear water, or it's interesting because I don't even know if they're still running. Somebody told me that they went back to gravity with the HTPSR system. I don't know. I don't work there anymore. But the HTPSR pumps are closed impeller pumps. But the openings are gigantic. If you ever look at those impellers and when they're out, they have a suction side sealing surface. And then the side portion, there's like a huge opening into the discharge loop for those pumps.
Mr. Crew, I'm pretty sure that the filtrate pumps and filter press are closed as well.
Yeah, they probably would be. Yeah, I don't remember offhand, but yeah, they're probably, because the expectation is that it's supposed to be clear water, and they are the most efficient. Then if you consider and think about how much filtrate gets pumped through them, and look at the size of the motors, and then compare the sludge pumps that recirculate the sludge and look at the size of those motors. it shows you how efficient, much more efficient those closed impeller pumps are. But it's, yeah, there are impeller blades and then there's shrouds on both sides. Now, like I don't know that there are any left at the Valley. You guys might want to check it out. They're double suction split case pumps. I don't know if there's any down there. Where there's a single impeller, and the case is defined as a split case because the top portion of the housing it's basically a flange type connection with the bolts. The video that I showed you guys with the guy with the glasses was talking about the packing and the pumps. That was a split case pump. Those pumps are actually, we'll say, easier to work on. But then again, too, once you separate those two halves of those pumps, you got to make sure your gasket it's sealed up pretty good. But you can look at the whole package. From it's not an end suction pump. It's called a split case pump, and they're usually a lot of times they're dual suction. So the impeller's on the shaft, but the suction's coming in from both places. Those are also usually closed impeller pumps. They're also designed so that there's not a lot of thrust in the shaft because there's no pull. The suction's coming in evenly from both sides. So one side of the thrust movement is neutralized by the other side of the thrust movement. And then, of course, the discharge comes out. But I don't know if there's any split case pumps left at the Valley. There used to be the old STP pumps, the effluent pumps at the STB used to be split case pumps. I don't think they are anymore. I don't know what they've been upgraded to. But those are closed impeller pumps. Closed impeller pumps are usually for clear water or for cleaner solids. So just for definition, an open impeller pump is for larger solids. Semi-open is the impeller vanes with a shroud, and it's for medium-sized solids, which is, anyway. Closed impeller is for pretty much clear water, and that's where the impeller vanes are enclosed on both sides. All right. Now, this is something that you don't see too many. Well, you do. These are for high volume, low head applications. They're not going to create a lot of pressure, but you are going to be able to move buco water with these type of pumps. They're called axial flow pumps. It's essentially a propeller in the pipe. And it can be mounted vertically as well as mounted horizontally. So if you don't have to create a lot of head pressure, but you have to move gobs of water, an axial flow pump might be the solution for that. Now there's another pump which is a mixture of the centrifugal and the axial, and I'm going to show you, let's see if I can find a video on it, but it's this nonsense. It's called a mixed flow centrifugal pump. There's a couple of different styles of this. Actually, if you want to see one live and in person, take a walk to the EPS and go downstairs and look at the effluent pumps. The effluent pumps are mixed flow pumps. What they do is, this is basically a radial centrifugal impeller mounted in a vertical pipe. That's the simplest way. They do make them where there are impellers that start in a radial flow and then discharge it axially. Another good example is what's called a turbine pump, which is essentially a mixed flow pump. Okay, they have the in between. They can move gobs of water, and they can move it with some resistance or some head pressure. They can develop head pressure so that they can overcome resistance. Not as great as a centrifugal pump. And sometimes the lines get blurred between which pump you would prefer as opposed to which pump that you have. Now, like a turbine pump, which is multiple stage bowls set up on a shaft, it's usually a deep well pump. The motor is going to be up top. Then it's going to be a shaft all the way down to the bottom, and there's going to be a series of centrifugal bowls that are in stages that discharge, say, one into the second one, to the third one, to the fourth one, to the fifth one. And then there's a vertical pipe that discharges it up to the surface and into an elbow and then into the system. Those are supposed to develop a lot of pressure. Because the impellers are in stages, they do develop a lot of pressure, as well as high flow. And that's why water systems use them, because they need to develop pressure, because you have to have a specific pressure. You should have pressure in your water system, just out of safety. I think the rules say the bare minimum should be 35. You're allowed to spike down to 20 occasionally in an emergency, But usually you expect, I don't know, 50, 60 PSI at least to be maintained throughout your water system, because you have to consider volume and pressure and fire protection. So you got to fill up the water mains, pressurize the water mains, and then have that water go through all the water distribution system to not only feed people's houses, but you need to have, say you have storage tanks that are high in elevation for emergency water supply and to maintain pressure. You know, because God forbid there's a fire, the pressure goes in the toilet really quick. You know, you have like half a Burglar County opening up on a big fire, your pressure's going to dive, which kind of happened. What was the name of it? The paper company that burned a few years back.
Markel.
Markel Paper, right? Where it was famous. I mean, half of Bergen County was there. And the other half was in the other people's firehouses who were at the fire, you know? So I can imagine the water usage there, right? It was off the chain. So that's a big deal for a water system. So they have to maintain pressure and volume. Mixed flow pump, or that's not, it's called a turbine pump. By virtue of the way it works, by virtue of the way it flows, it is a mixed flow pump, because there are individual centrifugal bowls, as they're called. It's also called a bowl pump, discharge radially from the first stage to the second stage to the third stage to the fourth stage, however many stages there are. And they're all on a common shaft. The motor's up at the surface. So it's discharging radially, but traveling vertically. So that's mixed flow. If it kind of does a little bit of both, it's mixed flow. So it will pump volume and it can develop head pressure, which is what's needed many times, especially in water systems. So that's a mixed flow pump. So a radial flow pump, most common, usually discharges off to the side, comes in and then out to the side. A mixed flow is a little bit of both, and an axial flow is basically parallel to the shaft. Now, eventually, yes, it's going to make a turn, but it's basically a propeller in a pipe. And I don't know what this video is, but I'll tell you what I'm going to do. What time is it? Oh, it's almost, I don't know what video this is. So I'm going to leave it off here. It's like 10 of. And then we're going to talk about hydraulics next time we get together. Which today? Today's Tuesday, right?
Yeah, it's Tuesday.
We'll get into a little bit of hydraulics. And I hope this is a little bit more interesting. I think it is, from math.